So I believe we can start. And so welcome to this last morning session of this very nice workshop. Let me take this opportunity to thank Helmut again for the very nice organization and the Lagrange Center for hosting us. So the first talk of this morning will be given by Hans Singer. I've understood that this will be a sort of mathematical and signal processing rhapsody. So Hans.
Thank you very much again. Thanks for the organizers giving me the opportunity. And having the talk in the morning gives me a little bit chance to discuss the maybe questions that I would like to raise in this talk. So in a way, you will feel that it's like a tour through Europe in 3 days. So it's a huge field that I would like to cover. And normally you would take the historical path and say, well, you know, Fourier analysis is 200 years old. And then we had all these developments and now we are where we are. But I had a lot of interactions and the people in the room, some of the people in the room are testifying this. We had a lot of interaction with the engineers, and one of my standard statements nowadays is Fourier analysis is the same name, but it's a different object if you talk to engineers or to physicists or to mathematicians. Mathematicians take a pride of being precise, but physical relevance is maybe sometimes not so much important. And what I really try to do is to develop a new view on Fourier analysis. So if you're start to think that might be not so unreasonable at the end of the talk, I would be quite satisfied. So I call it a perspective talk. So it's not I'm telling you new results, more or less. Hopefully there are many new things in the talk, but it's not so much a given problem that we know all and which has not been solved so far, and we are trying to get better partial answers, but more a new perspective on the situation. In order to establish not only the connection between this event and Vienna or Austria, I would like to remember some of my early visits to Paris. I saw one of the very early preprints on wavelets by Yves Meyer, which is shown here. And I thought I have to find out what this is. At that time I was giving a talk in Nancy and came up with Yves Meyer. He had only 1 hour, he felt quite sick or so, but he told me, you know, function spaces per se are not so interesting, which was more or less my topic, but they have to be dealing with operators. So you're interested in Calderon-Sigmund operators nowadays. We know why wavelets are so important, because Calderon-Sigmund operators are the important operators. Wavelets are diagonalizing them in an approximate way. And the function spaces, luckily, were the right ones, the classical ones, Biesov-Triebel-Sorkin spaces. And I was taking another track in the years following with the short-term Fourier transform, and with Charlie we had this Corbett theory. I'm not going in this direction, but I wanted to make this connection at least. Now, if you're, I call it provocative statements, if you're looking at the mathematical side, some of the important things that we are doing here is, well, the Hausdorff-Young inequality. Is it a strong or a weak statement? I like to have discussions, but just a short question. What does it tell you if a function is in L5? Is it really useful information or not so much? How stable is it under perturbation and so on? Physicists tend to talk about the continuous basis of the Dirac measures, and they do some hand-waving arguments, and most mathematicians, including myself, say, well, this is very sloppy, it should be replaced. You can do it in a distributional setting, but then the setting is a very general one. Do we really need the full-blown theory of topological vector spaces, including the nuclear Fréchet spaces, which help us to understand that a in this continuous basis, any operator has an integral representation, which is the so-called kernel theorem in the sense of Schwartz. I had some interactions in the last few years with people promoting the so-called rigid Hilbert spaces. So people studying unbounded operators like differentiation operator, harmonic oscillator or so. And of course, it's very natural to take the Schwartz space there, which is a topological vector space with a countable family of norms. But I hope to demonstrate a little bit that you can have a much easier access with different tools from time frequency analysis. And the last thing I would like to mention is when you're dealing with, when you think that the Hilbert space is the most important space, of course, the most general operators are the bounded linear operators on the Hilbert space. So taking the spirit of operator ideals, you're talking, well, maybe some operators are better, Hilbert-Schmidt operators, they have L2 kernels, trace class operators are even better. But if you think in terms of smoothing, I mean, you project on a boxcar function, on a rectangular, it's not really a nice function. It doesn't increase smoothness. It's not a regular operator, even if it's a rank 1 operator. So kind of these are the questions, and the directions in which I would like to go is to promote what I'm calling conceptual harmonic analysis. And as you know, I grew up in the world of abstract harmonic analysis. Let G be a locally compact abelian group with dual group and the Fourier transform and so on. And then I went to the engineers and they were saying, well, the computer only allows finite vectors. So we use the FFT, of course, without any discussion. And the integration of these fields where I'm asking how well can I approximate a continuous Fourier integral transform by discrete ones. So essentially it's a question about approximating operators by finite rank operators, which I can not only describe on paper, but which I can realize in a computational way up to some precision. Then there is the Banach-Gelfand triple. It's kind of, I was lucky to discover that there is a function space which has some minimality property. So S0 is still my use for what is called the Feichting algebra. In Charles' book, it's M1. It's the modulation space M1. And it's the minimal space among all those function spaces which are invariant under time and frequency shifts. So if you take LP spaces, shift is isometric, multiplication with a pure frequency is isometric. So LP spaces are all between the smallest space and the dual space is the biggest one. I found it convenient after a while to call this space the space of mild distributions because it can be characterized by the fact that it has bounded short-term Fourier transforms. So if you are taking a tempered distribution, you can define the short-term Fourier transform. And if it's bounded, you're in this space and all these things are in between. So this is, and I would, there's a time, you can work with these functions and I call these elements also, I would like to tell you that for me, signals are members of these things. Signals are, to jump ahead, signals are things that can be measured. Now, what do you expect from a measurement? That if you add some signals, that it's compatible, but also if you take an average of measurements, it should be also measurements. So it's a bilinear mapping between those two spaces, and then maybe you can even forget about the Hilbert space in between. You have a pairing, and the space of signals is the space of mild distributions, and these are the test functions. You are not, in the test functions, allowed...
You distinguish between the signals and the sensors that produce.
Well, the sensors are the measurements.
Say that the sensors are these are functional.
No, this is exactly the change of perspective that I took in the last few years, that I think that normally you would say you have a function space and these are all possible functionals. But now I would like to switch. The point is, I mean, we're somehow discussing, maybe I go into this directly now, that L2 is the space, is very natural, signals are of finite energy. I mean, how can you have infinite energy? I'm saying, looking at the waves at the ocean, sitting oceanside, the waves are going up and down for millions of years or so. It's finite energy, hopefully, over finite intervals. So if you don't have a tsunami or so. So it's more something which you can maybe not directly measure. And sometimes I take my microphone and show you how the audio signal, which is something like this, it doesn't have really point values, but you can measure it, and I can show you the spectrogram. And it's bounded and can be displayed or so. And to say that you can measure with S0 means, for example, you can take any piecewise linear function, which is compactly supported, with finitely many nodes. All these functions are in this space. And everybody knows that you're never starting from a sharp thing with another sharp thing. So either you have a Gaussian approach or so. And even the people who are doing MP3, they are saying, well, we cut out from the CD player 512 samples, but then we make a smooth boundary because at the end you're doing short Fourier transform locally. Okay, so I shouldn't get too much into this. So this is just the abstract for records or so. So when we are talking about the field in a wide sense, then we can talk about the history, we can talk about the technical things. So when do two functions have a convolution product, by asking when is it pointwise almost everywhere defined. I think this is absolutely not necessary because convolution is an operator. If it's well defined on test functions, it's only the question whether it can be extended to a larger space, like an LP space or so. We can take the engineering viewpoint or physics viewpoint. I mean, I just jump here. In the last few years, I was exposed to discussions in so-called quantum harmonic analysis, but at the end, it's just what I have been discussing with Werner Kotzek in the late 90s, before when we were preparing our book, which means, well, operators are like their kernels, are like images. So you're doing a time frequency analysis of operators and nothing more, but we'll see it a little bit. Yeah, I thought that one of the questions that may make more sense to establish the connection between the fields is to ask what are the tasks that we want to do. And I also like this idea that, well, if we don't have a formal definition of what a signal is, how can you say what we want to do with these signals? And my comparison is from general real life. I mean, if we don't have a formal definition of what health is, how can you tell me or tell other people what healthy life is? And I think we all know that there are very clear rules what is healthy and not healthy, maybe not in the sense of a proof or a definition, but in the practical sense. So this is meant to be signals in the way how we understand it in the vague terminology, but what we want to do, and I want to correlate this with what we are doing in mathematics. So is something that we would like to do at a practical level related to the mathematics that we are developing? That's more or less my question. So we want to analyze, to receive signals, transmit it. Communication theory is very much about this. We want to detect, that was certainly one of the highlights of time frequency analysis in the last decade, detect very weak signals, namely gravitational waves, in a very noisy environment. And the LIGO experiment, which gave the 2017 Nobel Prize in Physics, was exactly using time frequency methods. It was using discrete families of discrete Wilson bases, as I have been working with Helmut on this. We would like, this is not possible within these talks, we would like to describe solutions to the Schrödinger equation. And it turned out that nowadays many papers have been written, including nonlinear Schrödinger equation, where all this time frequency stuff is just the right setting. So to have invariance or stability of the solutions or so. It's just good instead of time domain or frequency domain to look at the problem in the phase space domain, and then you can do many things. I also tried to understand, or still try to understand, more things about optical systems nowadays. So the question is, what are the things that these people in optical science are doing, and they are able to realize certain things that we call the fractional Fourier transform, the Fresnel transform, or so, highly oscillatory things. But if you take a time frequency point of view, you have to discuss the so-called metaplectic group, which my advisor Hans Reiter was starting already. And again, there's a big gap between understanding the functions or the function space is invariant under the metaplectic group and the practical realization. So I always would like to have a MATLAB experiment showing what I can expect, some mathematical analysis showing that this is not just a phantom, but it tells me exactly what we can do. And with exactly discrete Hermite functions, fractional Fourier transform, metaplectic groups, this was the completely mysterious side which is not accessible to computations. But nowadays there are tons of papers, they call it the linear canonical transformation group or the offset linear canonical, and they do it in a purely discrete way without reference to the continuous world. And so there is a lot of things to be done and to investigate it. So I will probably skip this. Yeah, maybe mentioning the fifth point. That's again something I learned. The understanding I have is going back to the discussions with Werner Kotzek from the Technical University of Vienna, who was then with me for a while, for several years. I mean, it's so natural to say, well, if you have a PDE with constant coefficients, then you can describe it through the Fourier transform using tempered distributions as a multiplication with a polynomial. Now, when you want to do variable coefficients, you say it's just the same thing, but you're describing it with a variable convolution kernel. Now, if you have this idea, then it's not so far to say, well, but you could also try to explain it by the transfer function. So you have a time variant transfer functions. So usually I'm saying, well, a moving average means you are having something moving around like this. And if it's changing over time, and at each point I write down what is the transfer function, so the Fourier multiplier, realizing the operator at this point, I have an idea what could be done. And so the question is, can we describe the Korn-Nirenberg symbol in some way? Or, and I think that's for me the other axis, where the discrete and the continuous are coming together. The symplectic Fourier transform of the Korn-Nirenberg symbol is the so-called spreading function. If you have a different normalization, it's very close to the discussion of Weil quantization and Wigner distribution, but I prefer the spreading function. Just think of matrices, which are in the finite discrete case, the operators. So any given operator has a matrix representation. Matrices form an algebra, and this is an n-squared dimensional subspace, a space of objects. Now we have the time shifts, which are n cyclic shifts. We have the frequency shifts, or you can say the multiplications with the rows or columns of the Fourier matrix. So it's n squared such operators. If you normalize them, they're unitary operators. And can you write every matrix as a sum of these time frequency shifts? And that's exactly what you can do. Yes, in the Hilbert-Schmidt context or with the Frobenius norm, they form an orthonormal basis. And the spreading function, telling you that every matrix is a sum of matrices which are side diagonals with pure frequencies in it, is some representation which is useful. Now, the Korn-Nirenberg symbol is something that is the symplectic Fourier transform, and we know the two-dimensional Fourier transform plus some inversion or so are harmless. So this also preserving all the information, and it's a matter of practical of practice, which of all these many representations are more useful for a given task. So I just put into this this slide the information that if we have the proper setting that allows us to make the transition from finite dimensional to infinite dimensional, then we can transfer a lot of things that we understand easily in the sense of finite linear algebra, also in the continuous setting. So what are typical things? We have a basis. A basis allows you to describe vectors in the coordinate system. We have linear operators. We store the information about linear mappings by writing the images of the basis vectors into a rectangular scheme, and we define matrix multiplication just to make it compatible with the composition of matrices. So if you are given a linear operator, a linear map from finite dimensional space, you write the square matrix and then you invert it with some algebraic computational manipulations, and you invert the linear operator, of course, because that's exactly the same. We learned, and especially when I do Gabor analysis experiments, that sometimes it's not possible to have structured orthonormal basis or even basis, because in the continuous setting, Balian law tells you it's not possible to have a Gaborian Riesz basis for the signal. So Gabor thought that taking the Gauss function integer time frequency shifts is a good way to expand in a unique way all signals. Well, you can have discussions, but at the end it turned out no. At the critical limit, you do not have both benefits, but you have both problems. So it's both unstable, and you really don't get all the signals, even with bounded coefficients or so. So this is why the concept of frames, or Banach frames, as I prefer to see it, or Riesz sequence or Riesz projection sequences came up. But in the MATLAB world, it's very easy. The dual frame is nothing else of a system of column vectors. You take the pseudo-inverse and you transpose it, because the pseudo-inverse has this format of a transpose matrix. So if you have 100 vectors in the 50-dimensional space, I would say or maybe you have 5 vectors in the 3-dimensional space, which span the space, so they are in a general position. You write these 5 vectors in a 3x5 matrix. The pseudo-inverse is a 5x3 matrix. You put it back and you have exactly the columns of the pseudo-inverse. But if this was a linear independent system, you would say there is a bi-orthogonal system. So a linear combination of those few vectors which are linear independent, which you get by inverting the Gram matrix and getting the dual thing. So it's just, it's not so easy, of course, a transition to the continuous setting. These are the right terminology. In the continuous case, you have to ask for estimates which are automatic in the finite dimensional case. That's, so to say, the trick. Because you may have systems which are dense, but the better you have the approximation, the larger the norm has to be. And that's a situation that doesn't allow you to go to the limit. Whereas, of course, frame expansions allow you to take every element as a convergent sum of the building blocks, like, let's say, Gabor expansion. And if you say the approximation is not good enough, you just add more terms. And of course, you would like to have that the big coefficients are more important than the small coefficients, which again is a situation different from what we see with Fourier series and LP spaces, as Temlyakov was showing us. So where thresholding is not a good idea, but okay. Now I jump again a little bit and go to the pictogram that I'm using to say what the Banach-Gelfand triple is. It's just 3 spaces, space of test functions, which from the signal perspective, these are the measurements, the linear functionals on this big space. And it's good to remember for your functional analysis course. Actually, I didn't learn it there, that what are the functionals on the big space, so on the signal space, which are represented by the elements of the predual. These are exactly the weak star continuous measurements. So if you say, well, what are trivial harmless elements here? A Dirac delta is harmless. It's a functional, S0 is only consisting of continuous functions. Now you have the Dirac at x, and then you have Dirac at x plus epsilon. You would say they're close to each other, but in the norm, they are far apart. But in the sense of the measurements of the weak star, they are close to each other. So kind of, if you measure the signal which is completely concentrated at x or x plus epsilon, you expect, of course, to have something similar and to exclude all the others. So to say the bidual space is not unreasonable, I would say. Yeah, maybe I should say also, without showing a slide, this is establishing a category, and the category means that the objects are triples of Banach spaces sitting inside a dual Hilbert space and contained in a dual space. The embedding between the little one and the second one should be dense, and weak star in the outer space. We all know, looking at the yellow object, if this is a separable Hilbert space like L2 RD, then it's isomorphic to a little L2. You have orthonormal bases, and then the natural Banach-Gelfand triple isomorphism is you're saying, well, these are the elements which have absolutely convergent expansions, and then you extend it by duality. This is really not new, because Norbert Wiener was saying, if this is the Hilbert space of all square integrable functions on the torus, then the inner object is the absolutely convergent Fourier series, A of t. And then people came and say, well, we have a nice Banach space of continuous functions on the torus, and we would like to study it by studying the dual space. Now, this is the space of pseudo measures. It's a little bit larger than the space of measures. And then distributions theory was developed, and they were saying, oh, these are distributions, and they have L infinity Fourier coefficients. But it's just another way of establishing this. And at the end, you could even skip the yellow object and just say, we are extending the operator from absolutely convergent Fourier series to Fourier coefficients, or even better, from little L1 of Z to the functions on the torus in a nice way, such that I'm getting an extension which is weak star to weak star continuous. So this machinery, which is the same machinery, of course, that people use in temporal distribution theory, is quite useful. I didn't tell you, I think it's not really necessary in this community, how the space S0 arises. So we have the short-term Fourier transform, and I assume, well, we know that it's isometric in the L2 sense, so the energy that you have in your signal is the same as the energy on the frequency side, but here you are spreading the energy in the time frequency spirit. So the short-term Fourier transform in the L2 setting is giving you something which is square integrable and bounded by Cauchy-Schwarz. But if it's integrable, it's a little bit stronger, because everybody knows something which is decaying, and if you square it, it gets smaller. So some guys are like a boxcar function, sinc function. They are not integrable, but if you square them, they're becoming integrable. So this is really, this condition, S0 norm, is really an extra condition. And it's maybe good to know that all the summability kernels that appear in classical Fourier analysis are satisfying this condition. Please. Oh, yes, it should. Yeah. Thank you very much. It should be, of course, the S is the frequency variable, should be put here. And yeah, that's it. Thank you very much. Yeah. So this G0 usually takes some Schwarz function, but the definition doesn't depend on this. But maybe you should think of a Gauss function. You're moving it over your signal, so you're making it integrable. Or you can take a distribution and you apply it to a time frequency shifted function. Yeah. But thank you. This is nonsense. And so you could say that even if it's a f is a distempered distribution, you can give this a meaning, and then you get for the dual space exactly boundedness. Yeah. Yeah, and we have all kind of properties. A spectrogram, it's like looking at the score of a piece of music. If you play the same piece of music a little bit later and at a different frequency, it's the same integral. You can smooth it out, and it has especially the tensor product property, which gives, the tensor product property here, which is the basis for the kernel theorem. So every linear operator from S0 to S0 prime has a kernel. So it has, in the sense of distributions, a continuous, a distribution, a mild distribution representing this operator. So somehow I told you my view is nowadays signals are element of S0 prime of the time or free, the ground space or so, and operators are general objects, mild distributions over phase space. If you take now the kernel, then you have something which corresponds to the matrix. But there are these other representations, and I think I can come to this. This is the key point. The operators from the small space to the big space. So maybe you are interested in operators from LP to LQ, from L2 to L1 or so. Then, of course, you can restrict it to S0 and continue it in a trivial way, and it has some kernel. Even identity operator, you would say it's a unit matrix, and that should be a Dirac along the main diagonal. These are all objects which you find here. Another good thing is that, well, up to smoothing, such objects are decent functions. So if you convolve it with the test function, it's very much like Schwartz. If you convolve it with S0, you're getting a multiplier, pointwise multiplier for S0, so at the end you land here. But everything is Fourier invariant, and convolution, of course, goes to pointwise multiplication. Pointwise multiplication goes to convolution or so. So you can do all these things. And one article I did in this setting is to redo all the things about sampling that I learned from Paul Butzer in the setting of this. The Dirac comb has a Fourier transform, which is a Dirac comb, which is not surprising. It's exactly what you expect from what you learn from, derive from Poisson formula. But you have to say this space is much bigger than the Schwartz space. So to say that in the distributional sense that I have, it's kind of a more narrow system. You are allowing many more test functions. So Poisson formula is valid for S0. And the counterexample that Jean-Pierre Cahan and Le Maurier were producing were possible with some mild decay in time and frequency. And Charlie showed the counterexamples are exactly possible in this setting if and only if you're outside of S0. So it seems to be the practically largest, reasonable, easy to describe space having these properties. Maybe I try to come to this picture. So now I'm taking the MATLAB world. I took a random signal. I take a discrete Gauss function, and I take the spectrogram, so the short-time Fourier transform. Some people study the behavior of this. These are the zeros here, so you can try to count this, and they have a nice pattern, so they are nicely spread out. There's no place without these zeros. If you count how many they are, it's about n. And so that's a very interesting subject. How are the phases going? This is an absolute value displayed or so. But a typical task of regularizing is, well, take a Gabor expansion, so a discrete version of this in time frequency plane, and add only the terms which are corresponding to an inner area. And now in the regularization I told you is you to first multiply, maybe you convolve first, you're taking a strip here, so you're making this part here, and then you're concentrating in time. So it's very similar. And that's also telling you, well, essentially, if you make this bigger and bigger, you're getting this. And I'm telling you this joke if you want. Well, people are selling you a CD and say, this is exact piece of music. But it's only exact for us who are unable to hear nothing any more than 20 kilohertz. I mean, with age, it's much less even. And it's for the 3 minutes. So This is the piece of music in the concert hall viewed by a bat. This is what we have on the CD, but our ears are only able to take this. And this is very much what you have also in image analysis. We're producing these pictures. They, from the distance, look like a continuous one. Maybe we sit in the movie, we see discrete sequences of discrete pictures, and we feel we are in the landscape moving in a continuous way. So I think that's exactly the way how you should say, this is a good approximation. For all practical purposes, it's like this. So you can say, well, how would such things converge to these things? How would a sequence of finite lengths converge to constant one? And you would say, well, you just get more and more ones. And the observer who is watching 25 coordinates after a while would say, well, I'm completely satisfied. So mathematically, it's the weak star convergence. Practically, in this picture, where the functions, the functionals are represented by bounded functions on the phase space, you would just say, if for every compact set and every epsilon you have a good approximation, so it's uniform convergence is norm convergence, uniform convergence over compact sets is the weak star convergence. That's exactly what we have. Now, yeah, so this is the definition of the dual space, and I would like to show you that, yeah, this is, skip this today. I would like to show you one of the MATLAB routines that I'm using quite a bit, and it's just the way of how to represent an operator. So if you think of a convolution operator, so some engineer is telling you we have a translation invariant system, and in the discrete case it's an operator commuting with cyclic convolution, then of course it has to be constant along main diagonals. That's very easy. Now, how does such an operator look in the frequency domain? So we take more or less the two-dimensional Fourier transform if you want, and then we know it's a diagonal matrix. So this is a concrete example with so to make it not so bad, with a continuous smooth kernel. That's why the diagonal, so kind of, you would say maybe I was convolving with a band limited function, so that would be the transfer function here, and the transfer function is concentrated. That's why you see only part of the diagonal. But you can also say it's a moving average with constant profile. So instead of looking at those profiles, I align the profiles here. So this is showing you the trend. Well, actually, I was saying this is band limited. So this is the transfer function written in this way. So here we have the time axis, and that's the transfer function at every given point that displays this. So it's constant, of course. A slowly varying function would have slowly varying things here. But we all know that in the finite case, an operator commuting with translation is the sum of pure translation operators, and they are aligned here. So this is you can say here you see the impulse response completely concentrated on the time axis. Here you see the transfer functions, here you see the matrix representation, and here you see the Korn-Nirenberg symbol. Now, what I learned and what is relevant for mobile communication, and that's again work with Franz Lawacz and Helmut and so on, is there are operators which are underspread operators. So they have a concentration in the time frequency domain. So a slowly varying operator typically may have, in mobile communication may have a small rectangle. So you have a little bit of Doppler effect due to the change of the profile, and you have some maximal delay, but I took this experiment. Now, what does it mean in the representation? You don't see very much in the Korn-Nirenberg symbol here because I was choosing a fairly large domain here, but you see these are banded matrices. And of course, the question is, how can you approximate such operators? How can you handle that? And why is it relevant or so? And now there comes the importance of the Korn-Nirenberg symbol. If you're taking such an operator, it could be the projection on a Gauss function, and then you're moving the element, and you say, instead of projecting onto the Gauss function here, I would like to project on the Gauss function there in time frequency space. So how would you do it? You would take your signal, move it to the position here, then you project it and you go back. So it's conjugating your projection operator with the time frequency shift. But conjugation with the time frequency shift gives some strange phase factors here, but the Kohn-Nirenberg symbol says it's just translation. And that's where nowadays the people who are doing quantum harmonic analysis, they say, oh, in order to establish a Gabor multiplier, we just have to convolve the projection operator with some other symbol, with a weighted Dirac, for example, for Gabor multipliers. So there is a discussion which says, well, if we do what we are used to do with signals, namely convolution, create Fourier transforms using a convolution theorem, is exactly what we do when we are dealing with building Gabor multipliers. Now, this is another example, and so we have this for representation. I should jump to the final part because in order to tell you, it's not just, I couldn't remove this quickly before my talk. The point is, it's not only, yeah, maybe I mentioned this before. When you do, if you have a signal which is concentrated in time and frequency to the left, then it's very plausible that in the time frequency picture, periodization means that you copy it to the left and to the right. So we all know if you have a coarsely periodized function, you can recover it almost by cutting out the mid part or so. But under the Fourier transform, periodization is the same as sampling. So if you do a periodization and a sampling at the same time, you're creating from a well-concentrated object something like this. Now, if you move things far away, every integrable function is more or less concentrated on a compact ball, and you have a good chance to recover approximately from a coarse, the function in a zero, of course, from a coarsely periodized and fine sampled thing. The good thing is if you do this in such a way that the sampling rate is the inverse of the period, then it's even FFT compatible. So the Fourier transform of your function in the Fourier transform sense of continuous functions is, after this procedure, going to the FFT, and that's actually how I produce the discrete Gauss functions. We take a Gauss function, periodize, sample it, and then it's invariant on the FFT, normalized, of course, in the appropriate way. So this was one thing I wanted to mention. Jump to this. Yeah, sorry. This is what I wanted to remove. Now, I think I wanted to tell you one more thing, but maybe I stop here. So to summarize, I think with this viewpoint that S0 prime or the mild distributions are the appropriate setting for signals, we can try to do all the manipulations that we do with signals. We can filter them, we can store them up to some resolution by taking Gabor coefficients, so discretization. But there are different levels of discretizations. Discretization is first done at the phase space level. So instead of having a continuous inversion of the short-term Fourier transform, we're discretizing in phase space, but they are still continuous signals. But if they are nice, then we are doing it in the discrete setting, and we are coming up with a finite dimensional approximation. Okay, I see something that has disappeared, but I can tell it in the last word is, with this approach, I'm also now able to do discrete Hermite functions. And how do I do the discrete Hermite functions? I use the fact that continuous Hermite functions are joint eigenvectors to localization operators. So if you take a short-time Fourier transform with a Gaussian window, so exactly something that we have seen, and you take any radial symmetric weight, then the common eigenvectors of all these operators are the continuous Hermite functions. Now, if you see the pictures, you can imagine I can build such operators in a discrete setting. It's no problem using Pythagoras to make radial symmetric weights on the two-dimensional torus. And with the help of this Kornierberg connection, which can be done in discrete and continuous, I am able to build matrices. The eigenvectors of these matrices are what are for me, and I'm quite convinced, the correct discrete Hermite functions. With these discrete Hermite functions, I can define a fractional Fourier transform, which are Hermite multipliers, which are just phase factors, pure frequencies. And now the invariance of the Wigner transform is something that one also would like to demonstrate. And again, one has to have a discrete model of the Wigner. And I was just, for those who are interested, normally you learn that it's only possible to have Wigner discrete Wigner for odd functions, or maybe even prime powers or so. I think I have now a way using this kind of MATLAB viewpoint as a beginning. The same thing for even functions. And I hope on Monday in Zurich I will tell at least Helmut a little bit more about this. But those who are interested, maybe just come up and let me know. Thank you very much.
Thank you, Hans, for this nice panoramic view. So we have time for a few questions.
What is the point? What is the role of quantum theory in this whole context? I mean, why do they call it this way? To me, whatever I've seen to it is a kind of an extension by allowing more general action. So why is it called quantum?
This is something I'm asking myself also sometimes. The point was that we learned about this from a paper by Rainer Werner, who is a well-established physicist. And he was using this terminology, and apparently he was influenced by quantum theory. So he was telling or developing a mode of convolving operators. So if you convolve two operators, you get a function on phase space. If you convolve a function on phase space with an operator, you're getting an operator. But for me, it's nothing else but ordinary convolution on the Kornierberg level plus identification. So if you multiply a complex number with a real number, you get a complex number or so. Yes, but a real number is a complex number for most people. And if you identify it, it's just the extension of multiplication. So in this way, and but also people in data analysis are using this now to kind of to do a smearing in phase space or so. And for me, the whole quantum is, I mean, there's no, quantization is you have something on phase space and you would like to make an operator. And there's, for me, this is the transformation in the different descriptions. So there is, you transfer operators, property structures from one to the other. So here I take multiplication in the spreading domain and put it on operators. But you can put matrix multiplication and put it to the spreading symbol, then it's called twisted convolution. And all the properties that you derive with integrals or so are easily can be understood a little approximately by just playing around and saying it's identification at the appropriate level.
Can I have one more question? So, viewing things through your lens, is clearly motivated by signal processing. So you give all this framework in which you can consider operators. For other people, there are aspects of operators that are of predominant importance. For instance, it's a big difference whether you are looking at a compact operator or at just an invertible operator between two different type of spaces, and more so about the spectral analysis. These kind of can you map these kind of distinctions through your setting?
In this setting, I was trying to avoid weights. So if you put weights,
it's a weighted thing.
If you have their weighted things, so it's like you say, I would discuss Bezier spaces only with PQ with S equals 0. And there are, of course, mappings like the lifting mappings allowing you to move around or so. But I think the main point for me is to move to the phase space perspective instead of either time or frequency or any other representation. That's I think is the key point. And the other thing is, I think sometimes I feel that we're at the level when we have this setting of somebody telling you, well, you know, the Riemann integral is great. You can integrate any continuous function. And people like you or numerical analysis say, a limited class with an efficient algorithm is the most important thing. That is exactly.
Yeah, I'm worried about completeness.
Yeah. So kind of,
to
I
go
would
from
say,
Hilbert to
if you have inclusion mappings and you know something is working with uniform bound, then of course on a compact subset or on the unit ball of a compactly embedded subspace, it will be uniformly, and then you can try to make a more efficient algorithm or predict the speed of these approximations by using the right function spaces. But they are, unfortunately, or fortunately for me, they are not the weighted LP spaces, the Sobolev spaces or so. They are the modulation spaces. That's a kind of a slightly different world, but we have also seen here that. But I think we should.
Thank you. Unless there's a last quick question, in the interest of time, I propose that we move on and thank again Hans for the talk. So we'll continue with a talk by Franz Lawatsch on Bayesian regression combination.
Oh, yeah. Okay, yeah. So I'll restart. Good morning. Thanks to Helmut for organizing this great workshop, and thanks for inviting me. It's a big honor and pleasure. Thanks also to the Lagrange Center for the beautiful venue, and finally, of course, to Huawei for funding all this. Now, after all the richness of Hans' talk, you will perceive my presentation as shallow and superficial, I'm afraid, and it also shows the big gap between mathematicians and engineers. I'm an engineer, and it's really nice to think back that over the decades, in spite of this gap, Hans and Charlie on the one hand, and my group, of course, also including Helmut, somehow managed to cooperate in a nice way. So that's really a nice thing to look back. Okay, so my talk, let me see, this is not really, yeah, this is the laser pointer. Yes, yeah. So the title of my talk is Blind Bayesian Regression Combination, and it's joint work with Dan Waxman, who is a PhD student of Peter Duric at Stony Brook University, and also Günther Kolliander, who is with the Acoustic Research Institute of the Austrian Academy of Sciences in Vienna. There's a link to Remy, who is on the, what is called, advisory board of ARI. Yes, I'd like to mention, we call it this. All right. Sorry about my voice. So I want to entertain you with a very basic problem, basic regression or estimation problem. The problem is to estimate a random vector, we call it target vector t, from a data vector x. So this, of course, is the standard problem. And we want to use a Bayesian framework. So it's about Bayesian estimation. And that gives us a predictive probability density function. We could also call it posterior, and not merely a point estimate, t hat. So a full-blown distribution of t, and this is nice because we, in addition to a point estimate, which might be the mean of this distribution, we also get a characterization of the accuracy of the estimator. Good. Now, there are many, many methods for doing this with different models, but which of them is best? That's a difficult question, and our approach is here not to decide for any specific estimator or regression method, but to adopt a principal combination of multiple methods. And we will pursue a hybrid model-based and data-driven approach because the rule for combining the methods, on the one hand, is based on a Bayesian statistical model, so this is model-based, but the combination rule itself is learned from a moderate amount of training data. So it's really a moderate amount. We're not talking about millions of data points, maybe 500. To just train the combination rule. Good, so here's a picture. Here's a picture of the overall setup. We have an input data vector x, which is unobserved. We do not know the input to the estimators. Then we have capital K, what we call black box point estimators. That's also important. They are point estimators. They do not deliver distribution, just point estimates. These are called Y1 through Y capital K. These are observed. And the role of the combiner now is to map these preliminary estimates produced by the estimators into a predictive PDF. P of t, given the training data C, I will tell you afterwards what the training data are, and given the stacked vector of all the estimator outputs. Yes, and the result of the combiner is this predictive distribution of t. Yes, and this combiner, we call it blind, and that also explains the title of my talk, Blind Bayesian Regression Combination, because the combiner does not know neither the input x of the estimators, nor does it know anything about the estimators. It does not know the characteristics of the estimators. However, of course, it learns the estimator characteristics from the training data later. So before going into the details, let me give you some general features of the proposed method. As I said, the method is called Bayesian regression combination, or BRC method. It produces a predictive distribution using the outputs of multiple point estimators and a moderate amount of training data. It does not know anything about the characteristics of the point estimators or the input. It learns these characteristics from the training data. It is able to take into account also, or to work with, heterogeneous and also dependent estimators. I mean, dependent means that their outputs are dependent. And in the end, it tends to improve on the point estimation performance of the individual estimators. Yeah, but in addition, it also provides a distribution. Sorry. Good, this is the picture again. And some generalities about learning or training. The combination rule, as I said, is learned from the, I'm always getting confused with the buttons, is learned from the training data in a training phase. So there's a dedicated training phase. What is the training data? What are the training data? Well, it is on the one hand a sequence of observed estimate vectors. Yeah? So you could identify the sequence index n with time, discrete time. So we observe not only one stacked vector y, but capital N of them, yeah, and these are combined into this vector y 1 through n. And in addition, we also, in the training data, we know the sequence of corresponding true target vectors. So we know the solutions of the estimation problem in the training data. And this together, y1 through n and t1 through n constitutes the training data. Good. Once the training has been done, then we come into the test or inference phase, and we observe a new estimate vector. Remember, the estimate vector is the output of all the estimators for one additional time point, let's call it capital M plus 1. But of course, we do not observe the true target vector. Now, this is what we want to estimate in the end. And the task is now to infer the predictive PDF of this unknown target vector, given the training data and the new estimator output. And both combiner training and this inference of the predictive distribution are part of the BRC method. Oops, yes. Okay, now one thing is missing, which is really important, and this is a parameter. The statistical model really involves a parameter, let's call it theta. And now I want to introduce the parameter. And that can be done by using a trivial expansion of the predictive PDF that we want to calculate in the end, like this. And basically, this is the total probability theorem where I condition on some unknown parameter theta. And this parameter theta, by construction, affects the distribution of both the estimator outputs and the true target variable. And this is expressed by this distribution P of y and t and given theta. And now everything is now based on this famous expansion. Leveraging this expansion, the BRC method consists of the following two stages. On the one hand, we have the combiner training stage, where the goal is to somehow calculate the posterior. This is now what we call the posterior. It's the posterior of the parameter PDF, theta, P of theta, given the training data. So we want to learn this parameter distribution from the training data. This is the combiner training stage. And the second stage is the combination stage, where we, based on the already learned posterior parameter PDF, we want to calculate the predictive PDF from the newly observed estimate vector yn plus 1. Okay, let me now visualize both this combiner training stage and the combination stage. Once again, the goal of the combiner training stage is to calculate the posterior parameter PDF, P of theta given C, from the training data. This is a visualization. We have the unobserved inputs from 1 to time capital N. The estimators produce sequences of outputs, again from 1 to capital N. This goes into the training algorithm. The training algorithm also takes into account or is able to use the true target variables from 1 to capital N. And then the output is the posterior parameter PDF. And yes, please.
What's the rationale? The T's are the ones you're looking for. How can you use them?
Well, it's the training phase. It's the training phase. So we are able.
Have sort of high fidelity solutions or some system that you can.
Yes, yes, to train the combiner.
That you have faith in that this is an.
Right. Yeah. This is how we learn about the estimators. Otherwise, the estimators completely in the dark. Yes, in the combination stage, we want to calculate the predictive PDF. So this is now the picture for the combination stage. We have the new input, which is not observed, but the outputs of the estimators are observed for this new time n+1. Then we combine them together using, for the combination, the previously learned parameter posterior, and then we get the predictive distribution. And yes, as I said, the combination stage uses the previously learned parameter PDF. And why do we do this in these two stages? Well, the main reason I would say is that once we did the training, the learning of the posterior parameter PDF, we can use it several times for several different inference or combiner phases. Yeah? So you could think that we observe not only one yn+1, but many, maybe n+2 and so on. And so we can repeat the combination always using the same posterior parameter PDF. Good, so this is the basic, let's say, picture of the method on a more or less high level presentation. And now I want to go a little into the Bayesian model that we use to actually make it happen. And the main problem in the model is we have to somehow model the estimators. We do not know the estimators, but we need to establish some probabilistic model for them. So this amounts to the question, how does the observed estimate vector, which is the vector of all the outputs of the estimators at a specific time n, how does it depend on the target vector Tn? And of course, this dependency is random. And how do we model it? Well, we use a generative model here that says that the output of the estimators is the true target, well replicated capital K times, because we have K estimators, plus some mean, which is an estimator bias of the estimators, yeah, a mean, or we call it bias. Plus some additive noise, which is Gaussian, yeah, and we constructed it as standard Gaussian observation noise, which is normal 0I, multiplied by the square root of the covariance matrix. So in the end, of course, it's Gaussian noise with zero mean and this covariance matrix. Yes, so these are the two things that are now still unknown, the mean, the bias, and the covariance matrix. And of course, this generative model amounts one-to-one to a likelihood function of the observed estimate, which is the PDF of estimator outputs given the target variable and the parameter, and it's a normal distribution with this mean and this covariance. However, in general, the mean is allowed and the covariance are allowed to depend also on the target variable, not only on the parameter.
So, but you force it at all stages to be Gaussian.
Wait a bit. In the end, it will not be Gaussian, precisely because mean and covariance depend on the target. Yeah. Yes, in addition to modeling the output of the estimators, we also need, after all, we are in the Bayesian framework, we need a model for the target variable, a prior. And here we say, okay, the parameter does not act on the prior of t, so it does not, the theta does not enter here, and it's again a Gaussian with some mean and covariance, but since we don't know this, we use a weak prior, which means that the covariance has a very large variance, a very flat prior. Good. Now, putting these two models together, we can now calculate this important thing, which is the PDF of the joint PDF of estimator output and target variable conditioned on the unknown parameter. We just multiply the likelihood function and the prior, and we get a product of two Gaussians. But in total, this is not Gaussian in general, precisely because mu and sigma depend on Tn. Yeah, not only on theta but on Tn, and this dependence, as you will see, can be very complicated, and that's why we have a much richer statistical model than just Gaussian. Yeah. Okay, so once again, the observed estimate likelihood function is this. And now we need, these are the two important things now. And in the remainder of the presentation of the model, I really want to talk how we model, but actually this is correct. How we model the bias, the estimate bias, and the estimate covariance function. And also how we model the prior of the parameter, which is also a thing still to be modeled. Yeah. Also, the parameter is supposed unknown, but also random with a prior distribution. And you will see that choosing this prior distribution and modeling mu and sigma are somehow intertwined, so they cannot be separated. Yes, and we actually introduced several different models with different complexity. A basic distinction between these models is between constant models and GP-based models, where GP stands for Gaussian process. And I will explain these things presently. Yeah, constant versus GP. Let's start with the constant model. Yes, it's very simple. In the constant model, we just assume that the bias and the covariance do not depend on the target variable. That gives us Gaussian, yeah, but it's only the constant model. Yeah. Good. And we say that the mean, well, the mean is already part of the parameter theta. So the mean is the parameter is one part of the parameter theta, because the elements of the mean are just elements from the parameter. And these parameter elements are Gaussian, zero mean with some variances. The covariance is a little more complicated. As we model it as a product of a scale matrix, a diagonal scale matrix, and a non-diagonal correlation matrix. Yeah. The diagonal scale matrix looks like this. And the parameter, the other parameters, are, well, it's log normal. The diagonal elements are log normal, and they are IID with, again, some mean and variance. That's one thing, and the other part is the correlation matrix, which is again random, and is distributed according to the LKG distribution, stands for Lewandowski-Kurovitska-Joe, which is just one stochastic model for correlation matrices. Here is it's very simple. That's also the reason we chose it, probably. Yes. Yes, and now the overall parameter, theta, is composed of theta mu, which is actually the vector mu, really. Then the diagonal elements up to an x per log of the scale matrix and the entire correlation matrix, theta. This is the overall parameter. And since we also fixed the distributions of these parameters, we at the same time specified the prior parameter distribution. Yeah? So we have everything here. But again, this is only the constant model. Yes, please.
Is theta a parameter or is mu a parameter?
Well, we call everything then theta in the end. But, you know, theta consists of three parts. Theta mu is actually the vector of all the mean entries. Yeah? So actually it's mu. Yeah? This is a little confusing. Theta mu is mu of theta. Yeah?
Theta d is mu d and sigma d.
Yeah, the theta d is the vector of all these theta d1 through theta dkd. Yeah. And then we have just the correlation matrix, which is distributed like this. This is.
Maybe I'm just missing when you write that the theta d's are themselves random variables.
Yes, they are here. They are normal, IID normal. I don't understand the question now.
Okay, that's the prior on theta d.
Yes, yes. So this is the prior on theta mu. This is the prior on theta d, and this is the prior on the correlation matrix. It's sort of complicated, yeah. Good. Now, much more general is the GP-based model. And here we model the dependence of estimate bias and covariance on the true target variable, and it's modeled by Gaussian processes. And basically, we just replace in our previous model the thetas here by Gaussian processes that explicitly depend, but in a random way, of course, depend on the target variable. So now, and for the covariance matrix, we have again the same model as this product, but now the scale matrix, the diagonal scale matrix, scaling matrix depends on explicitly on the target variable. In a similar way as before, so we have again a diagonal matrix and we work in the exponential domain, but these are again Gaussian processes. The correlation matrix is the same as before, so no change. It does not depend on Tn in our model. It's again the LKG distributed correlation matrix. And now the overall parameter is the vector of all Gaussian processes here, of the mean, of the or bias of the diagonal scale matrix, and again the correlation matrix. And of course, this is not very pleasant because I call it parameter, but actually, as you might know, Gaussian processes is non-parametric, so there is no parameter. It's random functions, so these are really kind of wild monkeys. But fortunately, comes to the rescue that there exists by now a computationally efficient parametric GP approximation, which is known as Hilbert space GP, Hilbert space Gaussian processes. And this brings us back again to the parametric world. So now it is finite dimension, whereas Gaussian processes are, of course, infinite dimension and parametric. So in the end, we have a true parameter, and of course we also, since these are Gaussian processes and theta is LKJ, this again specifies the prior distribution of theta. Okay. Yes. So in addition, not in addition, but as a further specialization of the constant and GP-based models, we have what we call the independent model. It's very simple. We just replace the correlation matrix with the identity matrix. And this, of course, means that the overall covariance matrix, sigma, becomes diagonal itself. And it amounts to the square of the scaling matrix, of course. And this can be done in the constant case, which we call constant independent model, and it can also be done in the GP case. We call it GP independent model, where it still depends on Tn, but everything is now diagonal. Good. So this was the modeling. I now come to the inference, and there are two aspects of inference. Inference in the combiner training stage, which is really the learning, the training from the training data. And then there's also inference in the combination stage. And I want to briefly discuss this. So inference task in the combiner training stage is to calculate the posterior parameter PDF, P of theta given C from the training data. And this is based on a more or less trivial factorization, which is given here and can be easily established using, of course, some conditional independence assumptions, which I don't want to talk about. And our approach, or Dan Waxman's approach, actually, I have to say, he did most of the work. He's really mostly a sampling person, so he used the Monte Carlo sampling approach to do it. And so we characterize the posterior parameter distribution by samples, theta m, drawn from this distribution. And how do you do it in practice? Well, he used the nuts method, which is an adaptive version of Hamiltonian Monte Carlo. What? Yeah, that's good. And I like it too, even though I don't understand it. And actually, he did more. He used also an implementation provided by NumPyro, I hope I pronounced this correctly, which is an open source probabilistic programming language framework. And this is actually quite powerful because what you need to draw samples is just a generative model of the overall model. And we have this, you know, I told you previously, this is a generative model. So we have this sort of Gaussian generative model. And then this NumPyro can calculate just any conditional distribution you want. Yeah. Yes. Okay, so a little more complicated is the combination stage. Here we have to calculate the predictive PDF from the observed estimate vector yn+1, and also using, of course, the result of training. And we do another expansion. Expansions are nice. Again, probably based on the total probability theorem. And you see the posterior parameter distribution appears here explicitly. But we also have these distributions. So actually it's quite, well, for me it's sophisticated. We approximate this integral by a sum. And the trick is to take this into account by using the the samples we previously calculated and drew from this distribution. And then in order to take this distribution into account, we use weights that are proportional to this distribution. Why do I say proportional? Because we have an unknown proportionality constant here. And this is somehow taken into account by self-normalizing the weights. Yeah? Yes. And of course, this distribution is still there. Yeah? So this is the trick to do it. Yes, and then from this approximation, from this sum approximation, we draw samples. Tn+1 L from 1 to capital L. And this is again done using the nuts method in the end. Yes.
Going back to these weights.
Yes.
These weights are still just proportional with an unknown proportionality.
Yes, but it seemed.
Why don't you just take a Monte Carlo integration given the stochastic nature of your sample theta m? Wouldn't that reflect as well?
I don't know either. I mean, this is one method that Dan came up with. Yeah. Actually, this self-normalization trick takes care of this unknown proportionality. Yeah. Okay, so these samples now in the end represent the predictive PDF, approximately, of course, because we used an approximation. And now, once you have them, you can calculate a point estimate just as the sample mean, and this will approximate the MMSE, minimum mean squared error estimate. But you can do more because actually we have a complete predictive distribution. For example, you can also calculate a measure of uncertainty, which is given by the sample variance. Yeah. Yes. Okay. So that was the theoretical part. Coming to the numerical results, and probably having not enough time to do it right. But we compare 4 variants of our BRC method, which is constant independent, constant dependent, GP independent, GP dependent. So we have both the distinction between constant and GP based, and we have the distinction between dependent and independent. Yeah? And we compare it with 3 trivial, I have to say, reference methods. The naive mean is just taking the mean of all the estimator outputs. Yeah? This is one way, one poor man's way of combining them. Yeah? Just take the mean. Then the best individual is just we look which of the estimator outputs is the best, and then we just take it as the final estimate. And single on all data means we just take one estimator and it gets all the training data. Yeah? All right. And what are the estimators, you might ask? Well, we take random forest estimators because their performance depends not very strongly on the choice of hyperparameters. It's always difficult to choose hyperparameters, and that's why we choose these random forest estimators. But of course, the estimators could be anything. Of course, we get different results then. Yeah, that's the point. Yes, and in this presentation, we just use synthetic data conforming with the Friedman #1 regression problem. Don't have the time to tell about this too much. Just synthetic data, but we also did experiments using real data. Yes, and the performance measures are on the one hand MSE reduction, which is the reduction of the mean square error relative to the, well, actually this is an error, it's actually the best individual reference method. Yeah, so the best individual, not the single on all data. Sorry about the error. And the second is more sophisticated. It's what's called a calibration curve, which measures somehow the accuracy of the estimated predictive PDF. How good is the predictive PDF? Not just a point estimator, which is a point estimate, which is checked here with the MSE reduction, but the entire shape of the predictive PDF. And this is based on the concept of highest density interval of probability P. And it is able to evaluate the uncertainty, the quality of the uncertainty characterization provided by the predictive PDF in the sense of overconfident versus underconfident. Yes, so maybe I just present one of these experiments. I have 3, but let's just go for one in the interest of time. This is very simple. We have K is 5 estimators, and how are they trained? Well, we have a body of training, estimator training data. This is not the training data we use for training the combiner. It's the training data for the random forest estimators, yeah? Which is not really part of our method, this training, yeah? But we still have to do it. And the idea is that we split these estimator training data set into 5 disjoint parts, and every one of the 5 estimators gets one part of the entire training data set. Yeah? Good, and these are results. Well, what you see are the different methods: best individual, naive mean, constant independent, constant dependent, GP independent, GP dependent, and single on all data. And well, for BI, best individual, the MSE reduction is 0 because this is the reference. Yeah, the MSE reduction is with respect to the best individual, so there's no MSE reduction. And then the MSE reduction should of course be large, so larger is better here. And the colored dots show the outcomes of different trials. in addition, I also have the black stars, which is the mean. Yeah? So the black stars are the average performance in terms of MSE reduction. And what we can see is, first of all, maybe as expected, the methods allowing for dependency, modeling the dependency between the estimators or estimates are better in terms of MSE reduction than the independent methods. So where do you see this? Dependent is here, and these have a higher mean MSE reduction than the independent methods, which are here and here. Yeah? So this is better than that. This is better than that. Higher black stars. And it's also better for the GP-based methods that model the dependence of bias and covariance on T than for the constant methods. You see this here, the GP-based methods are higher than the constant methods. Yeah? But there's also one maybe unpleasant surprise. The highest MSE reduction is produced by the single on all data method. So if we just use one estimator, one random forest estimator, give it all the training data, the estimator training data, then it performs better than combining the estimators with disjoint training data. Yeah?
Okay, but right now you use the same estimator and train on the thing, right? Wouldn't it be more interesting to use different estimators and train all of them the same data and use the same?
What do you mean different? We have different estimators, right?
It's all the same method, all right? And then in order to make sense of this, you need to split the data, right?
Yes.
But just use 10 different estimation methods, train all of them with full data, and then you wouldn't see that, right?
So I have to emphasize that these results are pretty preliminary still. Yeah. And of course, we have to do more. This is also part of my outlook that I have to say we have to do more experiments, also including real data and so on. By the way, we also have one case where the single on all data is much worse than the other methods. So this is not a really general thing that the single on all data is better than our method and so on. Yes, but I want to remind you, even though this is maybe disappointing, it's still true that the single on all data method does not produce a predictive distribution. It just produces a point estimate, whereas our method produces a full-blown predictive distribution. And this can be seen in the calibration curve. This is the calibration curve. This broken line here would be correct uncertainty quantification. Everything that's below is overconfident. Everything that's above, but there's nothing above, would be underconfident. And what you can see is that the dependent methods are significantly less overconfident than the independent methods. These are the independent methods. These are the dependent. And why don't we include the reference methods? Because they do not produce a distribution. So we cannot draw the calibration curve for that. Okay, let me come to, I have to jump this now. These are the two other experiments. Yes, conclusion. Well, we proposed methods, actually it's multiple methods, but all in the same spirit for calculating a predictive distribution from the outputs of multiple point estimators, plus a moderate amount of training data. And these are not the training data for the estimators, these are now the training data for the combiner. The estimators do not have to be known. They are learned from the training data. They may be heterogeneous and dependent. The methods are based on Bayesian models, different Bayesian models that range from simple parametric to complex non-parametric Gaussian processes, even though in the end, of course, it's again parametric due to the Hilbert space approximation. And yes, training and inference are implemented in our methods currently by Monte Carlo techniques, and, well, limited numerical results confirm to some part the effectiveness of our methods. Well, outlook, well, the first point is further experimental evaluation comparison We might extend the estimators to soft output estimators so that they already produce a soft output. And for this, there are already existing methods that we could compare to. We could extend it to streaming data where there's also some dynamical model over time. For example, we could use, instead of Monte Carlo, variational inference techniques. And of course, we should more apply it also to real data and see how well it works. That's the end. Thank you. Thanks for your attention.
Thank you. We have time for a few questions. Wolfgang?
General philosophy. So, if you want to use a moderate number of training data, that means you have to have a very good model as a prior. So that very good model as a prior is your very involved construction with all sorts of processes, which depends on hyperparameters, which you have to choose.
Yes,
so
that's true.
In the end, if you do not have a ground truth to compare with, but is there a chance to get some kind of accuracy quantification? Because there are very many things to be chosen by you.
Yeah.
And so I'm just for your, I mean, you have much more experience with your view on this. Is that a realistic way? Because ultimately, in a huge universe, you are poking around to find a good prior. A good prior, because that allows you to get away with few training data.
Yes.
And that prior, however, involves a lot of things you have to choose, right?
Well, a lot of things not, I would say. For example, parameters of the Gaussian process are part of our parameter theta that we learn in the end from the training data.
Yeah, but in the end you have to project it to a finite dimensional setting, and this requires some presets, which is not right.
Of course, I would say so. Yeah.
And the second question on a conceptual level, you can view this as moving ahead in time.
Yes.
Right? So could you view this as in the framework of data assimilation and use concepts from there, where you have in the back sort of some discrete dynamical system which you move ahead and then establish your stepwise your estimates on the.
Well, I think that's what I meant. Extension to streaming data that has a dynamical model over time. But at this point, we don't know how to do it. I mean, we did not consider it. Let's say like this.
Okay.
Yeah? Of course, Peter Djuric is a big expert on, and also myself to some part on dynamical estimation and so on, using particle filters and so on. So maybe we will do it in the future. Yes. Yes.
Okay. Thank you.
Mm-hmm.
Do we have another question? So maybe I have one in reaction to the one of Wolfgang. If I understand well, the much of the modeling is done by the estimators that you combine first. I mean, these are the ones that capture the dependence between what they can access to and what's and your estimate. I mean, you're assuming that the estimators do not produce garbage somehow.
Yes, of course.
And so you're you have the limit.
No.
The type of modeling on the probability distribution is what is the noise that these estimators produce?
Actually, because of this, because we model the estimation error, we actually model the likelihood function where we have the generative model is really the estimation error of the estimators. And maybe I disagree with what you said. The estimators do not have to be good because we use these training data. So, the training data comprise the estimator outputs, but also the true target variable. Yeah. So as long as we have access to this training data, they characterize the characteristics of the estimators. And so the estimators' outputs need not be good. As long as we know this correspondence from the training data, we can correct it in our training phase. You know what I mean?
Yeah, yes, I
The
understand.
estimators do not have to be precise or accurate.
But then I guess I agree with Wolfgang that probably there's a hotspot where if the estimators are sufficiently precise, as relatively precise, then a relatively generic model of your error can fit. But if you try to handle arbitrarily bad estimators, then of course the structure of the model of your Gaussian process will probably hurt you in your capacity to correct.
Well, I'm not sure. The Gaussian process is a very general and expressive model. Yeah, that's exactly why we chose Gaussian processes, because they are a very expressive model. And I would even say if the front end estimators are already very good, really accurate, then we cannot gain anything by combining them. Yeah? But if they are bad, but the training data describe how they are bad, then we can correct for it, and then we can get a good MSE reduction, I would think. Yeah?
I agree about expressiveness, but maybe it's not only about expressiveness, it's about the balance between expressiveness and the sample complexity, the number of training samples you need to actually adjust to this.
Yes, of course, of course. We have to figure this out, yes, more. Yeah.
So, Holger? Sorry, Wolfgang. There's
same direction. So in the same direction, could it even be like if all the estimators produce random random estimates which have nothing to do with the truth, but during the training, actually your method basically gets to see the ground truth. So it may also construct an estimator, which in the extreme case may ignore all the estimators that you get, but just.
That's an interesting idea also. Yeah, that we. That's a good suggestion to look into this. Yes.
Yeah, because on the other hand, as input, this method as input just gets the outputs of these estimators.
Yes,
so,
in the test phase, in the inference phase, yeah, it just gets the outputs. It does not get, of course, the true.
Okay, so there has to be some information in this.
But I would say the estimators still have to exhibit some systematic behavior that can be learned in the training phase. If the output is purely random, yeah, then we cannot learn too much, I would say.
Mm-hmm.
Yeah.
Okay.
There must be some systematic dependence on the T, yeah, to learn.
Okay.
Yes. Well, I guess we should.
Did I get that right? That you benefit from a large variance for your priors?
Well, the T prior has a large variance because we do not know anything really about the distribution of T, or we don't want to assume any.
Okay, so you leave enough room. Okay.
Yes. This would be unrealistic to say we almost know the parameter and have a small variance. Yeah.
So I think it's time to thank Franz again.
Yep.
And we'll have a coffee break and we'll resume at 10 past. Thank you. So I think we can resume, and the next talk is by Gérard Mart.
Thank you.
Oh, I'm sorry, I forgot about the Venus connection, which is...
Well, today that's the easy part, to establish the Viennese connection, right? I mean, it's basically all Viennese today. Yes, so I'd like to chime in with all the other speakers to thank Helmut for organizing this great event. I very much appreciate to have the opportunity to present some of our recent work here. But even more so, I appreciate the amount of things that I've learned in the extraordinary talks during the past several of days. This is really a lot to take away from here. Now, in this talk, I'm going to switch gears a little bit. It's still kind of a different topic that other people have been speaking about. I'm trying to point out connections here and there. So the background here, I'm an engineer like Franz with a signal processing background. But there was a lot of talks about neural networks, and towards the end, I'll point out some connections to that as well. But the general theme that I'm going to talk about is what's known in our community as graph signal processing. So this is signal processing, data processing, if you like, where the data lives on graphs, and this has been quite a exciting topic now for several years in the engineering and signal processing community. And so what I'm going to talk about is actually joint work with my PhD student, Philipp Reingruber, and what we are trying to do is actually we were trying to come up with transforms at the end of the day, if you like, that are constructed from frames, and the key driving concern for us was actually computational efficiency, and I'm going to motivate why this is the case in this area of graph signal processing. So, having said that, this is maybe a topic that's not close to what many of you are working on and looking at. I'll spend some time to kind of discuss a little bit the background and motivation, what this is all about, and why we care. And so the basic scenario, super simplified here, is that, as the name says, graph signal processing. So there is graphs that are involved. So we have combinatorial graphs. I denote this here by G. This is basically a pair of sets where one set, the V, is the nodes, the vertices, which are shown here by red circles in this toy example. And those vertices are connected by edges or lines. And these are just the lines connecting here in the plot. And we're going to be general here, which means that we also allow for the edges to be weighted. So it's not just 0, 1s that indicate whether there is a connection or not, but these can be basically arbitrary positive real numbers. And if the weight is 0, it's basically indicating that there is no edge at all. And we're using these to model all kinds of practical engineering scenarios. So I've listed here several interpretations of what the nodes and the edges could represent in actual problems. So in the simplest case, the nodes will just correspond to individual data points in a data set, but they could also represent users in a network of people, or in real world, or in online platforms. They could represent devices, right? Could be smartphones or any other device. Any other kind of machine or plant could be represented by the vertices, even products. And then if you go biomedical applications, sometimes the nodes represent genes or brain regions and so on and so forth. So you see, it's a pretty broad spectrum that is covered with this generic approach. And the edges then correspond to establishing some kind of relationship between the nodes. right? And these relationships can be either statistical, right? So basically distributions or conditional distributions. They could represent social relationships, friendships, followers on online social platforms. It could be representing a communication link, or some biological signal paths, and so on and so forth, right? So you see that it's whatever comes to your mind, lots of things will fit into this general framework. And the generic goal of graph signal processing is to do signal processing on these kind of graphs. And so what's the major difference to conventional signal processing? Well, essentially what you lose is regular structure, right? I'm not saying you lose structure because there's still structure. The graphs will capture some structure, right? They clarify what objects are related and which are not, and so on and so forth, but it's no longer regular structure like you have in ordinary signal processing, right? Ordinary signal processing, you have either temporal signal, right, which is basically linear arrangements where essentially the graphs would simplify to be just line graphs, or maybe circle if you do cyclic, or in image processing, you will have regular grids. So there's always regular structure there, and we're trying to push this further to graphs that do not have that regular structure, but still tell us a lot about what's going on with the data sets that we're looking at. Okay, so I'm using, of course, here lots of signal processing language. Of course, I mean, if you're coming more from a machine learning perspective, it's still the same kind of framework. There, people would refer to the signals, so the data that lives on those nodes, they would refer to those as attributes or features. But at the end of the day, this is the same thing. Good. So, okay, this is just a simple example illustrating what's going on here. This is a random geometric graph where connections are just basically nearest neighbors, and you see the colors indicating node attributes, and we'd like to figure out certain things, right? So there's all kinds of problems that you can come up with. You can do clustering here, you can do denoising, in-painting, interpolation, quantization, and so on. So there's a rich set of challenges that arises in graph signal processing. So maybe to motivate a little more why people have started to look at graphs as the backbone, and apart from the fact that it's a good model, right, which is stated here on the left-hand side, where there is some structure that we can use, and specifically there is sparsity that comes into play. The edges usually do not connect all the nodes. There's much fewer edges than there could be in virtually all practically relevant scenarios. There is global behavior that emerges from local interactions between the nodes and so on. So this is very powerful, but at the same time, graphs also serve as computational workhorse. You have heard about message passing in the talks of Ruediger and Philip before, and most of the algorithms that we have are actually, or many of the algorithms are of that nature. They're extremely efficient, and at the same time, they're extremely well suited for distributed implementations. So if you have your graph, usually it's pretty straightforward to organize the calculations to have them on distinct platforms. Good. So a few practical examples just to kind of complete the whole application scenario. Here is a sensor network example. What you see here, this is China, and the black dots indicate the weather stations in China. Depending, you could again come up with the nearest neighbor graph construction here, given the coordinates of the weather stations. You could use historical data that has been collected by those stations to construct a graph, which is something we have worked on as well. So these kind of setups are suited for graph signal processing approaches. There is communication graphs. Here you see basically a portion of the internet with a still larger number of nodes and interactions, all kinds of routers and devices here connected. That's an obvious application scenario. Infrastructure networks have been looked at, specifically power grids. You see here the power grid, a visualization of the power grid in the US with all kinds of plants that you have, wind and solar here specifically, the edges representing the transmission lines and so on. Now, slightly different from that here, this is kind of a recommender system scenario, if you like. The graph that you see here is known in the community as the Amazon co-purchase graph. In this case here, what the nodes represent individual products on Amazon, and the edges represent, or they connect products that are often purchased together. Right? And the idea is that products that are purchased together, there is some kind of connection that this tells you. And we were actually using this to solve basically interpolation in-painting problems. So let's say, in this case, this is 1/3 of a million products roughly. And we were looking at scenarios where we basically just observed ratings for 1,000 products, and from that interpolated the ratings of all the rest, just exploiting the connectivity that the co-purchase information is providing you. Then there is social networks. Here you see the Austrian Twitter sphere a few years back. Nowadays, most of the people have actually moved to Blue Sky. Here's Armin Wolf, a well-known TV news host in the center with most of the follower relationships. In this case, the edges represent basically follower relations on that network. Something that we have started to look at as an important application scenario is data sets that represent point clouds. So if you think augmented reality and autonomous driving, autonomous vehicles, usually those are equipped with sensors that deliver data that's essentially point clouds. And then from the point cloud, you can again construct graphs and use the graph then to do all kinds of things. So specifically compression to store the huge amounts of data that are collected is still a big challenge here. And then finally here, I've referred to biomedical applications before. This is biological networks. This is the gene regulation network of the E. coli bacteria. This is a little bit different from what you have seen before in that there is red and green edges. So this is actually a signed graph where you have positive and negative connections representing activation and inhibition in the gene expression paths. Good. So, okay. Kind of having set the stage conceptually, let's dig in a little bit more into how we go about characterizing these scenarios. It's very common for the graph representations in graph signal processing to have a vertex set that's just the integers from 1 to n, capital N representing the total number of vertices that we have. This is basically just the labeling of whatever nodes you have in your application. And the edges we're going to represent in terms of the weighted adjacency matrix. This is an n by n matrix. The non-zero elements indicate the presence of an edge between two nodes. And as I said before, these might be potentially weighted. And a key object that we're going to use for graph signal processing is the graph Laplacian, which is essentially the negative weight matrix. On the off-diagonal elements here, basically these are the weights. And on the diagonal, what you put here is the row sums of the weight matrix, which is more or less the weighted degree of the nodes, right? So if the weights are just 0 or 1s, here you will get just the number of edges that are incident to a particular node. And this is known to be an important object with a lot of useful properties. So one of the things, for instance, that's important from a data processing perspective is that this Laplacian provides you with a notion of smoothness. So if you now have data living on such a graph, and the data I've organized here into a vector X, the elements are the signal values, if you like, on each of the vertices. If you compute the quadratic form with the graph Laplacian, what you can show is that this is equivalent to what's shown here on the right-hand side, which is basically a weighted sum of the square differences between neighboring signal values. So that means if the two signal values are close on the nodes that are next to each other, the difference will be small and the whole thing will be small. As a matter of fact, the smallest value that you can achieve is for a constant signal that has the same value everywhere. Then this will go to 0. So that's the smoothest signal that you could think of that has 0 variation. Okay. And this constant signal that I was referring to turns out to be actually an eigenvector of the Laplacian with associated eigenvector 0. And if you push that further, you get the successive minimizers being all the Laplacian, the eigenvectors of the Laplacian. And the higher you go, the larger the eigenvalues are, the less smooth the signal becomes. So it will be more and more oscillating on the graph. Okay, so that provides a lot of intuition about how we can think about data and signals on graphs. So at the end of the day, we can come up with an eigendecomposition of this n by n matrix. And the thing maybe to point out at this stage is that the Laplacian is very convenient that it's usually an extremely sparse matrix, right? As I said, not all edges that could be there are usually there. So there's a lot of zero entries in the Laplacian. But then if you compute the eigendecomposition, you lose the sparsity. And the eigenvectors, the sparsity will usually be gone. And this is going to be important for what's coming up. Now, what people have then started to do is, as I said, since these eigenvectors are successively more oscillatory, you think of those essentially as a Fourier basis, right? The first one is constant, so that's the DC component, if you like, with zero frequency. And then as the frequency lambda increases, you get more and more oscillating signals. And so what you can do is, for any data vector that you have, you compute the transform, basically just in inner products, and then you get in the graph Fourier domain corresponding transform coefficients that you can then use to resynthesize the signal. So this is basically forward and backward transform. And this is all kind of nice. It's consistent what we have to what we have in the traditional setup. If you have a line graph, this essentially, or on a circle, this will reduce to the discrete Fourier transform and so on and so forth. So all plays out. It's very nice generalization. It even allows you to come up with the notion of graph stationarity, where what you impose is that the statistical correlation of the coefficients at two different frequency indices vanishes, right? And then the power, basically, you can think of as a power spectral density, if you like. So it's kind of nice, and it has been the predominant paradigm for several years. People have designed filters using this approach. They have come up with sampling procedures and so on and so forth. But there is a fundamental downside, which we have observed led to a little bit of a kind of people starting to be less interested or maybe less excited about graph signal processing, which is that this transform usually is extremely expensive. Since it's no longer sparse and doesn't have any other structure in the general case, the complexity usually is quadratic in the number of vertices. And if you now think of large social networks with 10 millions of users, this is a no-go anymore, right? So there's something that needs to be done. Also, this graph stationarity notion is a little bit contrived in terms of signal models, so, but I'm not digging into that any deeper. The real thing that we were trying to attack is this thing here, right? We want to have something that's much less computationally expensive. Okay, so what we're looking for is a transformation that replaces this graph Fourier transform that does have low computational complexity, ideally building on basis functions that are well localized, right? This is going to be a key goal. And we'd also like to have some structure, right? Being engineers, we'd like to think in terms of frequency and localization on the vertex domain and so on and so forth, that allow us also to come up with some intuition about what's going on. The basis that we are looking at, we want to have some design flexibility there, but the design should be simple as well. And then, of course, this should be useful, right? The signal and data sets that we're looking at should be well represented in terms of those bases, possibly in the statistical setup, decorrelating signals as well. So there's lots of things that have been done. Not going to talk in depth about this. This is a paper that Remy has been involved, where people have come up with basis wavelets and filter bank type, which build on spectral designs. The idea being that the spectrum you live on, basically on the real line, and everything that you can do from ordinary signal processing, you can then start to do here in the graph Fourier domain as well. And this has some appeal to a certain extent, but from our perspective, the key driver, which is achieving low complexity, is still not satisfiably addressed by these methods. And there's another approach then that actually is more related to what we are doing, which builds on partitions. And the idea here essentially is that you split the overall graph into smaller subgraphs and then work on those subgraphs. And there has been work in that respect, but the deficiencies of these approaches are that while they do achieve low complexity, in general, they are not well suited because the partitions they are using are disjoint, and the basis functions that they come up with are not well localized, and also there's basically no design flexibility in their designs, right? So once you have the partition, this will give you the basis and that's it. And so there is lack of flexibility here as well. Say again? No, it can be arbitrary subgraphs. Yeah. Because you reduce the size of the graph. I'm going to get to that in a second when we analyze what we are doing actually on this slide here already. So that's the idea that we're actually sticking with, right? Partitioning the whole graph into subgraphs. The number of subgraphs I'm denoting by capital M. But the main step that we made that's different from all the previous work is that we allow those subgraphs to overlap, and this will actually turn out to be crucial to achieve all these other goals that I've been mentioning before. And then, I mean, this is something that to a lot of you with a background in Gabor and so on, harmonic analysis will be kind of obvious. What you do is you do windowed Fourier transforms on those subgraphs. Hans? Yeah, partition, I agree. Yeah. Good. So what we'll see is that this allows us to come up with overcomplete frames. I'm going to explain the construction in more detail in a second. And there's a lot of flexibility that this buys us. And as far as complexity is concerned, Ruediger, the thing is that what you're now doing is you're computing local graph Fourier transforms on the subgraphs, right? And they have a complexity that's quadratic in the size of the subgraph. But the sum of those squared complexities is usually much, much smaller than the square of the total number of vertices that you have, right? So the usual speed up that you get is actually proportional to the number of subgraphs that you design. And if you do this properly, specifically if you let the number of subgraphs scale like n over the log of n, then you can come up with a transform that's basically FFT speed, okay? Good. So, yeah, this is kind of illustrating the what's happening here in terms of partition with the windows that operate on the individual subgraphs. So here you see this would be one of the subgraphs. The color indicates the value of the window decaying from 1 in black to 0 in white with some roll-off in between. And if you look in this case, there is 8 in total. So the one I've shown you before was this one, and these are the other 7. And you see that they're overlapping, right? Some of the nodes are covered by multiple windows, and this is actually crucial for design flexibility and also localization, as I'm going to argue. Good. So let me explain the construction maybe a little bit more in detail. The basic gist I've tried to convey already. M is the number of subgraphs, and here essentially what we're going to start with is the window functions, right? So G is the window that lives on the subgraph M. N is the vertex index here, and those we assume have a finite support, right? So it's a small support that's denoted here by S, much smaller than the total graph. And the subgraph G that's induced by that support has size NM. That's just kind of the notation. And then we perform local graph Fourier transforms on these subgraphs, right, by basically just solving the eigenproblem for the local Laplacians, LM. And L will now be the local frequency index, right? So at the end of the day, if you look at these basis functions, UML, M will be indicating the location in the vertex domain, and L will represent the local frequency value, right? So for a lot of you, essentially the connection here is that you should think time and frequency, right? Computational harmonic analysis relating to Hans, right? And the basis functions we are constructing is just taking those local eigenfunctions and multiplying with the windows that we started out with, okay? And so maybe one comment here, the fundamental difference, so the thing that we have given up here and that after a lot of considerations actually we were thinking is the best to give up is that we do not have any kind of group structure here. It's not that you can shift things back and forth. If you shift this, you won't recover something that's living somewhere else and so on and so forth. But this is the price that at the end of the day we're willing to pay in order to end up with something that's both intuitive and computationally effective, right? And there have been other efforts, including what we were trying to do, where I think actually, I mean, if you want to insist that you have some kind of time and frequency shift structure on this, in the general case, it's not going to happen efficiently. Good. So, if we now take those basis vectors, these are the windowed local Fourier vectors, and arrange those in a matrix, the key insight actually that we had that motivated the construction is that if you look into the outer product of that matrix with itself, it turns out to be diagonal, and on the diagonal what you see is the sum of the squared windows, okay? And this is key because now if you look at this set of functions, ideally what we'd like to have is that those constitute a finite frame, and I mean, for lots of you, this will be kind of obvious. What you require basically is just that this does not go to zero, right? So in terms of frame conditions, the upper bound here in the finite framework is not a concern actually, but the lower bound is this must not go to zero. And if it does not, then turns out that this system here constitutes a frame. What that means intuitively speaking is that the windows must cover every node. There must not be any node that's not covered by the window, and that's the only constraint basically that you have in order for this to be a frame. So that's nice, right? It's already kind of useful and desirable that now we have a frame. You can come up with the frame operator then, which is just this thing here, which is diagonal. Now, one of the things then, of course, that pops up is that if you really want to do now frame expansions, you need the dual frame. And we don't know at all if we impose that kind of structure where, as emphasized here, this is now sparse because each of them has a lot of zero elements, right? Whether this structure is inherited by the dual frame, and as a matter of fact, it can be shown that it does, right? I'm going to show this on the next slide. Let me just say a word about redundancy. Usually, if this is a frame, this will be overcomplete. If you cover each point just once each vertex, then you will get basically a basis. But if the points are covered multiple times, then you have more elements here in that matrix than vertices. So you can have some kind of redundancy. The sum of the dimensionalities of the subgraphs divided by n basically is the amount of overlap that you have. And then exploiting the diagonal nature of the frame operator, you can easily actually show that the dual frame, the canonical dual, and the tight frame that comes with it, canonical tight, both are also local graph Fourier frames of the same structure, right? So the dual is basically using the same Fourier vectors, just a different window, which is the rescaled version, if you like, of the original windows with this sum of squares. And with the tight frame, you have the square root, is with all of kind of what's expected. So what's going on here essentially is if there is dips in P, so if some of the windows basically do not cover as well certain nodes as others, then those dips will be compensated by bumps in the dual window. That's more or less all that's going to happen here in the design. And the real important aspect about this is that both the dual and the tight have exactly the same structure. The windows live on the same support, right? So that means they have the same kind of sparsity pattern and so on and so forth, right? So all, if you start to do transformations, if you do analysis and synthesis with these basis vectors, exploiting the sparse nature, things can be done exceedingly effectively, right? So if you like, if you do the analysis stage computing the coefficients with the inner products with the dual frame, what it boils down to is taking your signal, multiplying it with the local windows, and then these local portions you transform with the local Fourier vectors. And the summation here extends only over the subgraph. That's kind of the key part that allows for computational efficiency. In the synthesis part, essentially, what you do is you have an inverse local graph Fourier transform, then you you basically have an overlap add procedure. Just multiply with the windows and add everything up. Okay? And as I've argued before, the complexity is basically the sum of the subgraph sizes squared, which, depending on how the partition is looking like, is usually in the order of n squared over m, so that's where the m-fold speedup comes into play. And if you look at this here, for instance, this is an example for random geometric graphs of increasing size. What we did here is the average subgraph size was fixed to 128, some a little bit smaller, some a little bit larger, but that's the average size. And then we scaled the graphs up to size 128 times m. And we looked into a larger and larger number of subgraphs. And then if you look at this, here you see the speed up of the transform relative to the graph Fourier transform. And you see that it's getting much, much faster here. This is M128. So this is a graph of size 16,000. And here you have a speed up of a factor of 120. So, okay. Let me talk a little bit about designs. I've talked now about the properties of those frames, how the windows, what properties they need to satisfy. The question is, how can we come up with windows of that type? And there are several ideas that we have floating around. Here is one specific that I think is very intuitive, which builds on an actual partition now, right? So this is now not the covering, it's an actual partition where you take the vertex set and you come up with subsets that are actually now disjoint. And the xi's here are chi's are the indicator functions of these parts of the graph. And what we're going to do is basically those indicator functions we'd like to smear out to create overlap, right? So in order to have some kind of roll-off, we'd like to smear that out, and this is something that in graph signal processing is well known. Essentially, you can come up with filters that create some kind of diffusion along the edges of the graph, right? The one that we have here specifically builds on the so-called random walk adjacency matrix, W tilde. That's basically the scaled weight matrix that has the property that the row sums are equal to 1. And then if you look at polynomials of this random walk adjacency matrix, the row sums of the filter that you create will also be 1, assuming that the coefficients in the polynomial also add up to 1. And that's the only property that we know that we need here, row sums of 1, because then if we take the indicator functions and smear them out with those filters, what you can show then is that if you look then at the sum of squares of the windows that you create that way, they add up to 1, so it's actually creating a normalized tight frame. So this is a kind of a very nice thing that immediately with very little effort you can get to. You can construct simple, nice frame. And the roll-off you can control with the filter order J here, right? The more, the higher the order, the more roll-off you will have. Okay. We can also control what the support of the window will be, because the filter order is J, it's going to be the J-fold neighborhood of the initial partition, right? So that's creating the covering, everything very nice and controllable. If you don't want that much overlap, because that will increase the redundancy, right? What you have to do is you need to shrink the V's that you created before you apply the smear out, right? That's the idea. So here, okay. Talking about partitions maybe on one slide. Also here, you might come up with partitions that are application driven, right? In certain scenarios, for instance, in the point clouds that I was showing before, there is, of course, you can exploit what you're looking at to come up with a partition. But in the general case, hierarchical spectral clustering will actually do a good job, right? So essentially what's happening here is that the initial graph, you split into two portions, essentially just computing the Fiedler vector and looking at the signs. This is classical thing. And then you just keep splitting the subgraphs further, right? So you take this subgraph, you split it in two parts, another one, and so on and so forth. So essentially you get a tree-like structure, and then you can piece together whatever partition you like. And as a matter of fact, what we were doing is we're showing that for those of you familiar with best basis selection, Kaufman-Wickerhauser, you can do the same thing here, right? If you have some kind of entropic measure on the quality of the partition, you can exploit that to optimize the partition as well. And this does not cost a lot, right? Because it's the Fiedler vector, it's the second eigenvector of the Laplacian. The Laplacian is sparse. You don't need it to full accuracy, you just need the signs, right? So it's not a big deal. And then all the successive ones are increasingly smaller. So it's really, in terms of computation, it's nothing relative to the rest of the design. Here's examples. This is a chittered grid graph that you see here. This is one of the subgraphs here, more or less the top left corner, if you like. This is just the indicator function, so this corresponds to a filter of order 0. In this case, you basically are critical, right? There's no redundancy, but the filter or the window that you get is just flat and then it decays to 0. So that's not kind of nice. If you start to smear it out, you see increasingly smoother windows. This is filter order 1s here, those two. This is filter order 2. And you'll see that it's going to start non-zero at larger regions of the subgraph. So you create the overlap, and that also increases the redundancy, right? So here there's 1.38, here it's 1.92. So, okay, there is some trade-offs here that you need to control. Good. So, okay. The last thing maybe to talk about is that I've argued quite heavily for the fact that the basis functions, the frame functions that we have, are supported on a small subgraph of the full graph. So we have super localization in the vertex domain, right? It's 0 outside of S, right? The other question then that arises is, what can we say about the spectral localization, right? Frequency localizations of the basis functions that we have constructed. And so we tried to analyze that because, I mean, this is something that we do not explicitly, or I mean, we do in a sense, but we wanted to understand how to control the localization in the frequency domain. So what you do is essentially you can compute the global Fourier transforms now of the basis functions, and then you just look at moments, right? So the first order moment will give you the center frequency, and then you can look into higher order moments to understand the spread. And what we found is that if you look at the first order moment, which happens to be basically just the Rayleigh quotient of the Laplacian matrix, then the center frequency is basically just the eigenvalue of the local Laplacian, of the lambda m, not of the global L, but of the local Lm, which is kind of nice because that's basically just the eigenvalue associated to the U's, right, that live locally on the subgraphs. Okay, and we could actually work out what the difference is between the two. It's given by this expression here. So the way you should look at this is the following. Here, this is the centered version of the local Laplacian. If the window is not there, if this is 1, then it's just the eigenfunction, which is actually in the null space of this centered Laplacian. So this will be 0. So the reason why it's not 0 is that... Okay, thank you. The reason why it's not 0 is that the window destroys a little bit the behavior of the U, right? There is some roll-off, so you lose something in that respect, but usually this will be close, so it depends more or less of how the window behaves here at the boundaries. And then, if you look at the spread, you can analyze something that we call the root mean square bandwidth, if you like. So here it's actually the square of that. So this is the centered second moment now in the graph Fourier domain, right? These are the global graph Fourier transforms of our frame vectors. And then we look at the second order moment centered on the center frequency of that function. And if you work that out, you get again two terms here that I'm going to explain. The first one is similar to what we saw before on the center frequency. It's basically depending on how well the windowed eigenfunction is still an eigenfunction of the centered Laplacian, right? So that means that this, in order to make this small, what you would like to have is that the window is actually constant on the support, right? At the same time, then there is a second term here, and this depends on the B matrix. The B matrix is the part of the adjacency matrix that connects the local subgraph to the rest, right? So these are the red edges here indicated in this illustration. And this second part actually depends on that, right? So it's kind of taking the local vector and look by how much it spills over into the neighborhood if you apply the Laplacian to it, right? And in order for this to be small, what you would like to have actually is that the window is decayed to 0 at the boundary of its support, right? So these two are in a sense conflicting, and you need to find a trade-off for both of them to become reasonably small. But that's kind of doable, and those two give you the criteria on how to accomplish that. A final comment in this context is that if those two epsilons here that this analysis gives us on the bandwidth, if those are small, then you see here that this we can equivalently express in terms of the squared centered Laplacian. So if this is small, it means actually that the norm of the Laplacian acting on the frame vector minus its scaled version must be small, which is nothing else than saying that the frame vectors are approximate eigenfunctions of the global Laplacian, right? Which is kind of a nice thing to get on top. Good. So, okay, here's an illustration of this. This is again on a random geometric graph. Just to give you an idea, what's plotted here are the global graph Fourier transforms of our basis vectors, our frame vectors, in the first subgraph, and L here is the frequency index, so this is the first, 46, and so on and so forth. It's 4 examples, and this is on a dB scale here, right? So you see specifically the higher ones, they're basically perfectly localized. The first one is a little bit spread out, but it's still very, very localized around 0, right? So this is kind of confirming that we have this kind of spectral localization. This is kind of illustrating this in a different way. Here, this is plotted now over all the basis vectors in the first subgraph. And what's plotted here in red is the center frequency. The green is kind of the RMS bandwidth on top superimposed. And you see that this is indeed very narrow in most cases. So that confirms that the basis functions are very well localized. And this is actually with smoothing. If you drop the smoothing and just look at the indicator functions, you see that the bandwidths go up substantially. So that's kind of, again, confirming this trade-off between redundancy and localization. Yeah, so talking about trade-offs, so this is kind of what we can take away of that. We have a lot of design freedom now, but of course we cannot have everything at the same time. So of course, I mean, certain applications you might have small redundancy. You care about how well the basis vectors or the frame vectors are localized. You care also about the frame constants, maybe aiming for tightness. And those are actually coupled, right? So usually you can only have 2 out of those 3. If you want to have low redundancy, this means little overlap. If you then also want to have things localized, so then you need roll-off. With little overlap, that means that basically it's not going to happen that you can have tightness because there is too little overlap to create this constant P that we need for that, and so on and so forth, right? So maybe in the remaining few minutes, let me mention what we're actually doing with this framework. The things that we have already looked at are the first 2 here. Graph signal compression. So if you have data on these graphs, think point clouds, right? Then, for instance, if you have color information for each of the points and you want to store that, you'd like to compress it, you can come up with a sort of a graph JPEG framework where you go to the transform domain, you apply the dual frame, go to the transform domain, do the compression there on a scalar basis, and then you can reconstruct with high accuracy. And this we found has work excellent. We did also look into signal denoising. If the measurements are affected by noise, then again, we transform domain denoising does very well for a lot of signal categories. At SAMTA, I'm going to talk about how to exploit this framework to do sampling and interpolation very efficiently, because everything remains localized. So it's still kind of the computational gain that's interesting here. And where we're trying to get to, that's kind of the agenda, is to use this to design filters. And the filters actually we're kind of seeing as a prerequisite for novel graph neural network architectures, right? So if you think convolutional neural networks, for instance, you know that at each layer you have basically a convolution, an ordinary filter operating on a grid graph if you do image processing. And if you now operate on a graph, you also need some kind of graph convolution, some kind of graph filter. And there's still a complexity issue with current architectures that we hope to be able to overcome by designing filters that build on these frames, right? So Gabor multipliers, frame multipliers, basically just multiplications in the transform domain. This is kind of where we try to go with this. Okay. We also found that the frames that we constructed are very good signal models. They allow you to capture non-stationary behavior, right? So the signal properties can change from subgraph to subgraph, which is a big advantage, I think, specifically if you look at large graphs. You can have different bandwidths in the individual segments and so on and so forth. So a whole bunch of avenues that's opening up here. So let me conclude by going back to the goals that I was mentioning initially. Okay, I mean, you might have suspected that this is coming up. I claim that we have kind of accomplished all. We have low computational complexity with well-localized basis function. We know that they characterize what's going on in certain portions in the graph from a spectral perspective. We have very simple designs that have a lot of design freedom. This is something that I don't talk about a lot, but we also observed that this works well in terms of decorrelating signal and serving as signal models. And with that, I'd like to conclude. Thanks for listening.
Prof. Gang?
So to really gain complexity, your M should scale with N, right?
Yes, so that's why, okay, let's see whether I can go there. But at some point I mentioned that if M scales with M over, sorry, here it is. If you let it scale as N over log N, then you will get basically complexity that's FFT-like, right? It depends on what you are willing to spend.
Yeah, but then the question is the quality. So you also need consistency, right?
Right.
So if you go to a continuous limit, the graph Laplacian would tend to the Beltrami operator on a manifold, if you had this model in mind. Now, is that still the same?
I don't know, but it's a very good question. We're going to talk, we are talking about the continuous limit with Charlie yesterday. You know, there is the Lovász graphon thing and so on. But this is not something that we have looked at. And it might be the proper framework really to, if you're interested in the scaling laws.
I guess it's probably true if you keep a moderate M, so even for fixed M, then it's probably true because that overlap will then shrink in terms of, but if you scale it with M, it may not be too obvious, right? With N, I mean, if you have, I see. Okay, thank you.
Thank you for your very clear and inspiring presentation. It was reminding me all over the place with what I have considered with irregular Gabor frames. So kind of the situation that you have here is that maybe the overall number of samples is too big and that you're doing a local reconstruction. And we had made experiments which are exactly in this spirit that you have given, that you're doing it locally. And if you split it into too small pieces, it's not good because you have mostly boundary regions. If you take it too big, it's not doable. The idea that also came up that we are computing, maybe not in the situation that you have approximate dual frames. Because if you think of 2D Gabor, the number of dual frame elements cannot even be stored, but it can be computed and approximate dual. And if you have a good computational machine, you could do a few iterations and still do with this tool very much what you do with the other thing. And there is this idea of uniform concentration or so the size of the boundary. If you have a global frame in Gabor analysis, irregular Gabor frame, the local concentration of the boundary regions is a fixed size. So which has to do with the window or so. And I think that would be nice to explore in your context. So kind of what if you add more terms to the graph inside, when is it not reasonable anymore to refine because you have already a good covering of the overall situation. And so I think there are many very interesting questions. Thank you again.
I agree with what you say. I see the analogy, right? And it might be also a good starting point to look further into these kind of aspects. I mean, the only thing, first of all, it's a much simpler setup, right? It's finite and so on and so forth. But then at the other hand, anything that exploits, time and frequency shifts and the underlying group structure is not going to happen here, right? So that's kind of the division between the two worlds. I mean, there's a lot of intuition, I think, that can be transferred. And I mean, the reason we ended up with that is actually all the background that I did learn from the old days working with you guys, right? But then at the same time, I'm aware that there's lots of structure that's also lost. Yeah. Ruediger.
One last question.
So you mentioned the Windows graph Fourier transform by taking a covering and suitably smooth windows. So the next step would be the construction of orthonormal bases in the style of the local Fourier basis. There you would have to choose. The question is that even possible to choose the windows in such a way that you have no redundancy and get orthonormality? On the real line, you can do that. For graphs, that might be an interesting problem.
My gut answer to that is no. The only one would be the one without smoothing. That's orthogonal, right? Yeah. And once you start smoothing, you get the overlap. And the thing is, I think the basic distinction is that the local graph, the local graph Fourier vectors that you compute, they live on the extended graph, right? On the support and not on the original interval. And they do not have all the structure that you have in Fourier, that these are translates and so on. There's just by phases and so on. Yeah. Yeah. I still stick with my answer that I think it's not possible. Yeah.
So right now, you take essentially whatever in a two-dimensional grid, you take still two-dimensional pieces, right? What is if you took paths, right? Then you would actually have not m squared, but it would have.
So
linear,
of course,
right?
the grid-like structure, this is mostly chosen for illustration purposes, I have to say, right? Because otherwise, it's very hard to kind of show what's going on. This is not fundamentally important. Where the kind of ideas that you're mentioning are important is that if you know certain topologies, so for instance, let's say you have a star graph where from each edge that goes out, you then have a path that's extending, right? So it's more or less paths that are connected at a single hub node, right? Power law kind of scenarios. Then actually, I think it's a good idea there to do the partition in such a way that you break off the individual paths, right? Because then on the paths, I mean, you can even fall back to ordinary Fourier analysis. And then it's just the intersection points that will then help you to piece together all the connected parts. Yeah. If that's what, I'm not sure whether I was getting to what you were asking.
One quick final remark. What is a problem let's say in the case of irregular Gabor? So we all know that the subfamily of a frame doesn't have to be a frame. Because the frame bounds if you take the part which is spanned like Gaussian, they are linear independent. 400 Gaussians span a 400-dimensional space, but by singular value decomposition, depending on where they are, which area they cover, they span much smaller space. So sometimes one has to refer to that space. Mm-hmm. And that's one of the reasons also why I look for discrete Hermite functions.
That's a very good point. I mean, subsets we didn't look at. Not very confident that there's a lot that's possible to say, but it's definitely interesting. Yeah.
Thank you, Gérard, again. Okay. And I think we're going to stop here for this series of questions. And to conclude the day and to conclude the nice workshop, I have the pleasure to welcome Charlie Groschenig.
So let me first test how to switch pages. Okay, how do I go back? And what's the pointer? Oh, okay. Okay, still good morning. I'll start with the preamble. First, thanks Helmut for the organization and invitation of this talk. And also thanks to Huawei for the generous sponsoring of this event. Second remark is this is joint work with Martin Ehler and Clemens Karner from University of Vienna. And you will see that all these nice pictures, they are definitely not made by me. So that's a very visible contribution. And third, there's a hidden connection to Lausanne in this case. Vienna is obvious, but Lausanne is a hidden connection. Let's see. Okay, yeah, there's a plan. So there's a hidden connection. It starts in Lausanne, and I think Martin Wetterli was thinking about monitoring of air pollution in Lausanne, and one option is to do it this way. You place many sensors at every block in the city and measure pollution. His idea was to place a sensor on a bus and let the bus drive around and just monitor pollution in this way. And this led to the idea of mobile sampling. You measure a field, a quantity along a curve, and this turned out to be a new idea, led to mobile sampling, and it attracted quite a few people to look at this. So my talk will be about mobile sampling on the sphere. Here's something we do discuss. So this is a room at the Acoustical Research Institute in Vienna. So you have a soundproof room. Somebody sits at the center and is exposed to sound from different directions. So here you see plenty of speakers focused on the proband, and well, this looks like pretty elaborate experimental arrangement, and well, you might want to replace, say, a few dozen of speakers by a single speaker and move that speaker around. So that's something, at least to motivate interest in this question, something one might envision. Wherever measurements or the measurement devices are expensive, you might want to switch to mobile sampling and use few devices and sample along a curve. So there's a third one, but that's a movie that I'm unable to integrate into the slides. You want to create low-dimensional portraits of a high-dimensional point cloud. You do that by projecting on lower-dimensional subspaces. And you want to find a suitable path through all low-dimensional subspaces so that you get a nice portrait. So that would be a third one. Third possible motivation. So mobile sampling is involved. So what are the goals? Now let me be more precise. Mobile sampling on the sphere. So we look at the d-dimensional sphere in our d+1, and so the abstract goal would be to approximate or reconstruct a function, a physical field, a quantity, or possibly just a functional of that function from the values along the trajectory of the curve. So you have, the information is values of that function on a curve, and you want to infer something about f, or possibly about a functional of f. The canonical functional would be the integral. And the abstract tools, or concepts, or definitions that the mathematical analysis gives us is either Marcinkiewicz-Zygmunt inequalities. We could also say there's some frame theory as a theoretical framework, or sampling inequalities. For the second problem, we would talk about quadrature rules. So you want to recover the integral over f. That's clearly quadrature rules and something similar you could do with other functionals. So these are the keywords: Marcinkiewicz-Zygmund inequalities and quadrature rules. So we're dealing with curves. So by this, in this talk, that's a map from some parameter interval into the sphere. It should be a closed curve, or at least a single curve, because the number of curves we use corresponds to the number of sensors. So for simplicity, one sensor, so one curve. Let's assume that it's closed. It's piecewise smooth. In some context, one wants finitely many self-intersections. In some contexts, one goes back and forth on an arc. So that I'll leave that open. So then the line integral would be this formula. So whenever this symbol comes up, and it will come up a lot, so it's basically you evaluate f along the curve. So you substitute the parameterization, multiply by the speed on this curve, and then you integrate over the parameter interval. In particular, the arc length is just the line integral of the constant function 1. So then, the important object is the distinguished subspaces of functions on the sphere. And for us, these are the polynomials of degree t. So we are in the D sphere. That's something in Rd plus 1. So pi sub t are the algebraic polynomials in D plus 1 variables of degree t restricted to the sphere. So there are some aspects that I'm not going to talk about. That's just the sort of the machinery of approximation theory. There are function classes, smoothness classes, usually Sobolev spaces, because then you know how well you can approximate a function with given smoothness by algebraic polynomials. And so there are some approximation theories that. So here I'll just deal with algebraic polynomials. Okay, so first notion to approach the problem of mobile sampling is we have a hierarchy of finite dimensional subspaces with polynomials of degree t, and we also have a hierarchy of, or we want to construct or understand hierarchy of curves, and I call a sequence of curves indexed by t, that's the degree of the polynomials, a Marcinkiewicz-Zygmund family of curves, well, for LP. If the LP norm sampled along the curve is equivalent to LP norm over the full sphere, and the quantizer is that should hold for all polynomials of degree t. And for every t, we have a different curve, possibly, and the important point is these constants should be independent of the degree t. If you may want to use p equal infinity for supremum estimates, then we take the supremum along the curve, and that should be equivalent to the supremum norm over the full sphere. The whole point is this constant here must be independent of the degree t. Well, for every degree t, I may need a different curve. If you just fix the degree and want a curve, if the curve is distributed densely enough, you always have that. Okay? But for a discretization procedure to finite dimensions, you always need this uniformity of the bounds. Does that answer the question? Yes. Okay, the second concept would be the concept of spherical t-design curves. In this case, we start with quadrature rule. So in this case, I omitted the, there should be a t here. So a curve gamma is a t-design curve if the normalized line integral along gamma t is equal to the integral over the full sphere with respect to the surface measure, and the quantizer is for all polynomials of degree t. So this amounts to a quadrature rule for polynomials of degree not exceeding degree t. There are no constants involved because we have equality here. So the constant would be uniformly 1. So the goal would be to construct a family of curves for every degree t, a curve that either give you exact quadrature or that give you Marcinkiewicz-Zygmunt curves, so that give you such a norm equivalence. Well, I started with curves, but clearly you should point of reference what is already known, or how does one do that with points. So when you do points, you have the same definitions. You have a Marcinkiewicz-Zygmunt array if the averaged LP norm is equivalent to the LP norm over the full sphere for all polynomials of degree t. Again, for every degree, you will need possibly a different subset. And in this case, the philosophy is if you sample densely enough, depending on the degree t, then you get such families. So this was, I think, for the sphere first investigated by Moskar, Narkovich, Ward, beginning of the 2000s. They were actually interested in quadrature, and they came up with Marcinkiewicz-Zygmunt inequalities for the sphere. Recently, there's a paper by Filbier, Hilscher, Jahn, and Ulrich, where they took up the topic. But the result that I would like to highlight is the other results from the group in Barcelona, because it's not just densely enough. They say precisely how dense you have to sample. So the condition is in terms of the covering density. So you have a set of points. So that's a finite, x sub t is a finite set of points depending on t. You take disks or balls of some radius large enough so that these balls centered at x cover the sphere. And if the radius is chosen some constant over t, such that these balls centered at x sub t cover SD, then you get a Marcinkiewicz-Zygmunt family. So for very small t, so first of all, the inverse scaling in the degree is to be expected. The higher the degree, the more degrees of freedom, so the denser you have to sample. What's really important is, here, there's an explicit number. This fundamental raise is less than pi half. Not just arbitrarily small, but less than pi half. And these results are complemented by results about interpolation. And for interpolation, they have another number that's not too far apart. So I think from that point of view, that's an optimal result. So when it comes to spherical, when it comes to quadrature rules, then that's a topic with a lot of history. So again, for a fixed degree t, you would call a set x a spherical t design if the average function value equals the integral of f for all polynomials of degree t. So the t design refers to the degree of the polynomials. One origin of this question is, of course, numerical integration. I think there were several other motivations to do that. The sort of the really seminal paper is by Delsart, Goethals, and Seidel. Existence of such point sets has been proved relatively early on. numerical constructions. There's a whole zoo out there. What's important is the existence came with sort of a huge number of points, and there was a conjecture that actually you should need to the order t to the d points. So degree of the polynomials is t, and d is the ambient dimension. So that was a conjecture, and it took 20 years and many, many attempts to say, yes, there exist t designs, spherical t designs with order t to the d points. And that's a great paper by, actually, they were diploma students at that time, Bondarenko, Radchenko, and Vyazovska. And it's a great paper. It's still exciting mathematics. So as far as existence is concerned, that's the best you can do, but that doesn't stop research because it's an existence theorem. And if you look at this line of research, man, rigorous proofs that some point set is a t design are quite rare, but you have t designs up to degree, I think, several hundred. So whenever I present a result, I should mention the analogous result for t design point for point sets. So it seems that these two notions are disjoint, but actually, in a way, they treat the same question. And this is sort of the I have to mention that it's known. And so let's see. So from t-design curves to Marcinkiewicz-Zygmunt, it's easy. So if you have a 2t design curve, so exact quadrature for polynomials of degree 2t, then you have Marcinkiewicz-Zygmunt identity, no longer inequality, but identity here. Okay, and this an if and only if. So that's just language, there's no mathematics behind it. If you take a polynomial of degree t, then f absolute squared is a polynomial of degree 2t. Exact integration implies that this is the integral over f absolute squared over the full sphere. And going back, you polarize. So polarization gives you exact integration for products of two polynomials of degree t, and then you look at the span. So what's important, I think, provides some insight is this equality here. So, well, this is still Marcinkiewicz inequality, but you have equality, the constant, now 1. So this kind of rigidity and imposes some kind of geometry on the curve. So the construction of t-design points and t-design curves is much more difficult than of the construction of Marcinkiewicz-Zygmunt points and curves, because there you have, say, perturbation theory and whatnot, and much more flexibility. So the order of difficulty is significantly different. So, secondly, I mentioned the mobile sampling problem. So if you have a 2t design curves, there's a formula for the reconstruction, and for Marcinkiewicz-Zygmunt you have some similar reconstruction formula. But let's see, for 2t design curve, so exact integration of polynomials of degree 2t, well, you take the reproducing kernel for polynomials of degree t. Then you take the product. This is a polynomial of degree 2t. You integrate along the curve. 2t design means that this is equal to the integral over the full sphere, and since it's a reproducing kernel, you get the function value. So in this case, there is a very easy and explicit reconstruction, and friends of special functions will know that the reproducing kernel is some kind of Gegenbauer polynomial. So this is as explicit as it can get. And secondly, there's a way to go from Marcinkiewicz-Zygmund inequalities for polynomials, or for anything, by the way, to quadrature rules. So this should be better known, but I don't really know what to cite except myself, and it's definitely incorrect. So if you have L2 Marcinkiewicz-Zygmund inequality for polynomials of degree t, then there exists a weight function just defined on the curve so that you get exact quadrature with that weight. This is, in a way, a bit cheating because we don't know whether that weight function is positive. It may be take negative values, and for quadrature rules, that's hated, I would guess, because there's some stability involved, but usually you want positive weights in quadrature rules. Okay, so t-design curves and Marcinkiewicz-Zygmund curves, in a way, address the same problem. So let me show you what, okay, so this is how you would construct that weight, but I think I skipped that. So before you start with constructions, better ask, what is possible? How much can you achieve? And what we found out early on is that if you have a t-design curve, so exact integration, exact quadrature for polynomials of degree t, then there's a lower bound on the length of the curve. And the lower bound is of the order t to the d minus 1. T again, the degree of the polynomial, d, the dimension of the ambient space. And there's a dimensional constant. It basically expresses the vague formulation. You have to sample densely enough, and in the case of curves, that translates into a lower bound for the length of the curve. When you compare to t-design points, then the number of t-design points for degree t is bounded below by some dimensional constant times t to the d. And this is plausible. You need at least as many points as you have dimensions. And so in this case, that's very plausible and predictable. The fact that you use a dimension here is something where that, well, you have to think about it. It's not, it comes from the proof, and the proof is not, is just imitating all these proofs for yes, that might be an argument. So underlying this talk is always the relation between t-design curves and t-design points. So what happens if you discretize the curve? Do you get points? And the other way around. So that's the underlying theme. So in a previous iteration, and that's what I talked about 2 years ago here and several other places, for dimension 2, for the 2-sphere, we managed to construct t-design curves with the asymptotically optimal length. So if t is equal to 2, then the length of the curve should grow linearly in the degree. So we managed to do that, and it's not so bad because for points, that's actually the resolution of the Correvor-Meyer conjecture. In higher dimensions, we didn't get that far, so we would be on this. We would be on the level of Correvor-Meyer in 1993. I should say that somebody at MIT, Ayo Lindblad, took up our work and managed to prove the existence, so of optimal, asymptotically optimal t-design curves for S3. He comes from geometry, projective geometry, and uses completely different tools from ours. So this is very exciting. And perhaps just one remark, we don't start from scratch. We actually use the construction of, or the existence by Bondarenko, Varjenko, and Vyazovska. Now, so far so good. Now comes the new part. I have given unusually many talks about mobile sampling on the sphere. I usually don't do that. Oh, yeah. So let me mention how the basic idea of the proof of t-design curves. You start with t-design points. You draw circles centered at these t-design points. So this gives you some spherical caps. And there is a connection on a eigenspace of the Laplacian. So these are polynomials of degree less than or equal to t, but have additional properties. The line integral along the circle is a fixed multiple of the point evaluation. So you can relate curves to point evaluation. And in that way, you put things together, you get t-design curves. Now here, in this picture, you haven't gained anything because you have as many curves as you have points. So that translates into as many measurement devices as you have points, so nothing gained. But as you increase the radius of these curves, at some point, the corresponding spherical caps will overlap. And that means these circles intersect. You still have the relation to exact quadrature, but now from these circles you can generate a single closed curve that gives you exact quadrature. And so this is the basic underlying idea, and then you start working. Now, a frequent question of the talks was, can't you just connect t-design points suitably and you're done? Well, the immediate answer is always no, because that's the first idea to try, and it never worked. So the immediate answer is, no, you cannot. Well, that's not the end. Well, what do you get if you try to follow this idea? That's one. So that's the topic for the remaining 15 minutes. And another question is, of course, when you say, can't you connect points, what do you mean by that? Well, ideally, when you connect 2 points in space and you don't think about it, you connect them by a straight line and not by some fractal curve or whatever. So when you don't think and you just ask how connect t-design points, then you implicitly think about connecting them along geodesic arcs, or on the two-sphere, that would be just segments of great circles. Okay? So, in answer to this question, what do you get? Okay, so connecting points along great circles means we start with these points. So we choose a set of control points in view of the original question. These are possibly t-design points. And then we connect these points along geodesics on the sphere. In the case of the two-sphere, these are just great circles. You don't have to think about geometry at all. And a curve that consists of geodesics connecting points would be a geodesic chain. And when you create a curve that visits every vertex exactly once and is a closed curve, then that would be a geodesic cycle. So that's just the terminology from complex analysis. And now we start with t-design points, connect them in such a way along geodesic arcs that we get a geodesic cycle, so a closed curve. Question is, what is that? Well, the answer is already suggested. Probably you get something has to do with Marcinkiewicz-Zygmunt, because we have enough flexibility. And so, but but I want to go a little bit back. You cannot connect t-design points and get a quadrature rule. So that I want to explain this no first and then go to the second question. So the easiest, bye-bye. So the easiest t-design points, spherical designs, are the Platonic solids. So tetrahedron, octahedron, cube, and some difficult words, icosahedron, dodecahedron. So these are t-designs for very low degrees. Fact is, the associated geodesic chains are not even one designs. So here's a picture. So here's a tetrahedron, 4 points. If you take the average value of a quadratic polynomial at these 4 points, then you get exact integration. If you take the line integral along this geodesic chain, it doesn't even integrate linear functions exactly. Same for all these Platonic solids. So there's always a geodesic chain that visits every vertex exactly once, and they don't even integrate linear functions exactly. Whereas the vertices give exact integration for polynomials of degree 2, 3, and 5. So that's an observation. And so now comes part of numerics. Usually the numerics doesn't fill much space in the write-up, but creates a lot of work. So again, my admiration for Martin and Clemens who did that. So the way you would create, so the idea is you take t-design points and deform the control points, and therefore thereby deform the geodesic cycle. And so there's a functional in the background, that's the integration error. So you have a curve. You look at the integration error for polynomials of degree t. So that's some functional. If you look at the geodesic chain, then that curve depends only on the vertices, so on the control points. So if you have n control points on the sphere, you have 2n parameters. So for geodesic change, this functional, this error functional, is a function of twice the number of control points variables. Okay, so you have 2 times n parameters. And so you can try to minimize that functional numerically with, well, I don't know, some optimization. Okay, so ideally you end up with parameters so that this error functional is numerically 0. Then numerically you have found n points such that the associated geodesic cycle gives you exact integration. Numerically that's fine, and then when you try to do that rigorously, well, you try to simplify that functional, reduce the number of parameters, and argue rigorously. So in that business, that's called beautification. So let me see what we get. So here's the case of the tetrahedron. So once again, the plot from before, the tetrahedron, associated geodesic chain. Now, 4 points amounts to 8 parameters that you have to minimize. So there's the art or the intuition of Martin. He saw that basically you reduce the number of parameters to 1. So you look at 4 points parameterized by a parameter A. For this parameter, arctangent square root 2, you get the tetrahedron, regular tetrahedron. Doesn't do anything. Now you start computing, estimating, and you find a parameter, 0.47 something, and the deformed geodesic cycle is then in fact a two-design curve. That's provable rigorously. Somehow the non-explained part is how do you reduce the number of parameters from 8 to 1? We don't have an explanation. You look at it and try to guess. Or at least that's, yeah. So here is a similar picture for 6 control points where you start with octahedron. So this, the associated geodesic cycle doesn't do anything for integration. When you apply the numerical minimization, after reduction to a single parameter instead of 12, then this is in fact a three design curve. So this process of beautification works for some platonic solids. You start with a 2 or 3 design, deform the corresponding geodesic cycle, and we can prove that these cycles are T design curves for T equals 2 and 3. So it's very, very modest. Here's an example where we don't even know whether these are rigorous 5 designs. Numerically they are. So anything explicit seems to be hard in this business. So I think now we come to the question, what do you get when you connect points to get a curve, a geodesic cycle? And you don't get T-design curves, but what you get, and that is sort of the answer to the question is, in general, if you start with points that are satisfy Marcinkiewicz-Zygmunt inequalities for points, and you connect them to create a geodesic cycle, you get a family of Marcinkiewicz-Zygmunt curves. I formulate this as an existence result because you need to start with Martin. So you need to start with points that are distributed densely enough, but in the sense of the group in Barcelona. Okay, so here's I formulate this as an existence result. There exist constants depending on the dimension, on the P for LP, and geodesic cycles, and okay, I never corrected this misprint. So a sequence of geodesic cycles such that this sequence of geodesic cycles is a Marcinkiewicz-Zygmunt family of curves for LP. In other words, you get this norm equivalence for the sampled LP norm to the full LP norm. The constants depend on dimension and the LP, but not on the degree. So the same constants for all degrees. And secondly, the length of these curves is bounded by T to the D minus 1. So that is well, you cannot do better than that, except for possibly the constant. So the length of these curves is of the order T to the D minus 1, and the order is best possible. Now, when you look at the construction of Bondarenko, Radchenko, and Vyazovska, they start with Marcinkiewicz-Zygmunt families that are distributed sufficiently densely, and then they apply some very, very smart deformation to obtain D-design points. And I could say if the points are defined, so this construction starts with points that satisfy Marcinkiewicz-Zygmunt inequalities. Can tell you exactly how dense they have to be defined. And then I think I will explain that construction plot. That's what obviously my doing. So you choose a partition of the sphere such that each patch of the partition is inside a disk of radius eta over t. So t doesn't show up. I do that for fixed t. You make sure that all these patches have the same area. So that's the so-called area partition. And you can also ensure that these patches are convex, or at least you can ensure that each patch contains a disk of a radius. So the outer radius is eta over t, and the inner radius is some rho over t. And then, so this guarantees that in each patch you have points that have a fixed distance rho over t. You connect such points, and then you go to a neighboring patch. Since these are adjacent patches and the radius or the diameter of a patch is of the order 1 over t, the distance from here to here is at least 3 times the constant over t. And then you create, so these are all geodesic cycles. So you move from patch to patch, and combinatorial argument tells you can do that in such a way that you get a closed curve. And when you count, well, then you estimate the arc length. So the distance is the order 1 over t inside each patch and to the neighboring patch. And you have t to the d points. So t to the d times 1 over t gives you a length of t to the d minus 1. And, well, why is that a Marcinkiewicz-Zygmunt curve? Well, you use mean value theorem. The line integral along this arc is equal to the point evaluation at some point along the arc. And so when you do that, just for the inner curves, inside this curve, there are points that satisfy Marcinkiewicz-Zygmunt inequalities. So that's a rough sketch of the proof. So Martin then went further. There's a rule. 2 authors take twice the time to write a paper. So he already wrote 2 or 3. So you can combine t-design points with t-design curves and look at hybrid schemes. So where one part of the rule is average over points, and the other one is a normalized line integral. You take a convex linear combination and you ask that this gives you exact integration over all polynomials of degree t. And the initial insight is that actually this increases the strength of the degree of polynomials that you can integrate exactly. So you get very nice pictures that I want to show that at the end. And he got up to, I think, degree 19. And even for rigorously proved t-design points, that's pretty high degree. So, okay, so picture. So strength 9, I think, yeah, okay, that's what I got from him. There's a lot to do. Some people think about replacing curves by submanifolds. The big open problem is getting the optimal order for higher dimensional spheres. You might want to use other manifolds, for example, Grassmannians. That's of interest when you do dimension reduction and portraits, low dimensional portraits. And yeah, we hope to do more on that. And yeah, something is on the archive. I should also mention that papers by Ayo Lindblad, they're also on the archive, should appear at some point. And perhaps somebody else will be interested sooner or later. With that, I want to thank you. And I finished on time.
Okay, we have time for a few questions. Maybe I start with one. Much of the bounds, I mean, in the design of these constructions, you consider the number of points or the length of the curves. But when you look at the type of construction, there's also a sort of diversity and covering, a sort of uniform covering of the sphere. Is there any necessary condition on this perspective, or could you have very localized curves but very space-filling curves?
No. When you look at the proof of the necessary condition, so there's a lower bound on the length, then you actually look at the covering radius of the curve, or you look at the covering radius of the point set, and you show that it's correlated to the degree. So you look at the largest whole, and that cannot be too large for both the quadrature and for Marcinkiewicz-Sigmund curves. So yes, there is more to it. For Marcinkiewicz-Sigmund inequalities and for T-design curves, they need to be uniformly distributed in some sense.
So it's quite different from the simple need to be able to, let's say, characterize the polynomial from sample values. It's really a matter of capturing the actual integral as a sum and not a weighted sum.
So maybe I elaborate. So think of points and a fixed degree. Of course, you need just sufficiently many points. They should not lie on any algebraic submanifold. So you could cluster them. Just many points clustering them, say, in the upper hemisphere. That's fine. You get an inequality. But as soon as you want to get uniform constants independent of the degree, that's going to fail. So that's where this families, the idea of using families and uniform constants plays a role. For a single T, there is no problem.
I mean, one way to do it would be to check that you find a curve between 2 points that give you exactly half. The integral is exactly half, or the average of the two endpoints, right? Because then this would, does that exist? I mean, can you always deform? So it's not going to be in general the geodesic, but is it true that you can do this independent?
That's a good idea. We did ask ourselves, how would you find a suitable curve between 2 points that does that? I don't know. But you're asking the right question, I think. But it has to be independent of the polynomial. And
okay, if there's no more question, let's thank Charlie again.
So at the end, it's time to thank the organizer for bringing us together and offering this great week here. Thank you, Helmut.
Well, I would like to reflect and pass on the thanks. So first of all, I would like to thank all of you for staying till the sweet end, the Viennese end we had today. And I would like to express my gratitude to the organizing team and to all those who supported us. Ijun, she is here in the back, and Wanjun, the two ladies who took care of everything. Xiaoyun in the background. Tanji, who started preparing the workshop, and he had to go to China. Shengling, he is here. I think I saw him before. There he is, yes. And Wenping, is he also here? I don't know. Yes, okay, good. So thank you very much. And then Shun Li and the whole IT team and Tua, who came all the way from China just to support us. And finally, I would like to thank the director of the Lagrange Center, Shang Ling, who sends his excuses. He had to run to China. And thank the Lagrange Center for the generous support. And before we go for lunch, I would like to hand over to Professor Laforgue, who will say a few words on behalf of Dr. Shangling Chui.
Yeah. So thank you. So I am talking in the name of the Lagrange Center. So our director, so Zhi Shangling, should have welcomed you, but he's traveling, not for pleasure, because it is part of his job. And I should have welcomed you in his name, but for personal reasons, I was not able to be there, which I deeply regret. So what I can say in the name of the Lagrange Center is that we were extremely happy that this conference was organized here by Professor Bolsky. So Professor Bolsky is visiting us regularly, and we are always extremely happy when he comes. And so it is not the first time, in fact, that you organize a conference here. And so the last one I was able to attend, even to participate. So it was a very interesting conference. And here I really regret that I was not able to attend at least part of the talks you have been giving. But once again, I think that everything was recorded. So it will be possible to look at your lectures. And I think in the name of the Lagrange Center that we will be very happy to organize other conferences like this one. So, but once again, I regret not to have been able to listen to your talks, but I could see from the program that the talks were very interesting. And so, in fact, I was only able to attend the last talk, which in fact was, I am a little exhausted, but the last talk was very interesting for me. And okay, so I once again, thanks to Professor Bolsky, and thanks to you all for coming from different countries, especially from Vienna, but not only. Okay, and so we hope, so the director, myself, other people from the Lagrange Center, who I see there are some of them here, both from the staff and from the people from the scientific side. So once again, thank you very much. And we hope that you will come again here for other occasions. So thank you. Thanks to you. Okay.
So, or similarly, go to your lunch. With your badge. Thank you.